an analog of Hardy inequality for the fractional Laplace Beltrami operator on Riemannian symmetric spaces of non-compact type. And this session will be chaired by Professor D.K. Ganguly. He is the Vice President as well as the Council Member of Calcutta Mathematical Society. So I request Professor Ganguly to start the session.
Thanks to the convener, Professor Kaushik Ghosh, to request me to take the chair of the session. Today, we have a speaker, very good speaker, Professor Dr. Sanjay Pusti, and Sanjay Pusti is my student, but he obtained MSc degree from the Department of Pure Mathematics. Then he got the PhD degree from ISI Calcutta, I think it is 2009. The area of his research work on the harmonic analysis and related topics under the guidance of Ruddo Sarkar, I think so, Ruddo Sarkar. Then he went to German to pursue the postdoctoral work. After returning from the German, he joined the IIT Kanpur Master Division in 2014 to 2017. He was there, and after that he joined the IIT Bombay in 2017. So we are very pleased to have such a speaker that is on the. We will talk on the harmonic analysis, especially emphasize on Lie group. So I request Sanjay Pusti to deliver his talk.
So thank you, sir. So first of all, I would like to thank the organizer and especially my friend Bablu for inviting me in this conference. And also it's very nice to see our favorite DG sir after a long time. So, okay, so I will start with my talk. Title of my talk is that an analog of, I think all of you can see my screen, an analog of Hardy inequality for the fractional Laplace Beltrami operator on Riemannian symmetric spaces of non-compact type. And this is a joint work with one of my friend, Mithun Bhaumik. Okay, so just let me start with that. What is Hardy inequality on a real line? So for that, first you start with if be a non-negative, compactly supported smooth function. Though these conditions is not that much needed, compactly supported smooth functions, but only to the existence of this integration. For that, I'm just assuming that it's compactly supported smooth function. Okay, so you assume that if it's non-negative and on 0 to infinity, then for any p greater than 1, this is the Hardy's inequality. 0 to infinity, then you take 1 by x integration 0 to x ft dt, then whole to the power p dx is less equals to p by p minus 1 whole to the power p 0 to infinity fx to the power p dx. Okay, so let me just a little bit give the outline how it proves. First of all, you see from the left side, if I start with this left side, I have written that 0 to infinity 1 by x 0 to x ft dt whole to the power p dx and then whole to the power 1 by p. From here, the next step, what is that? You just make a change of variable t equals to x into y. If you make a change of variable t equals to x to y, this first term will turn out to be this 0 to infinity, and then here is integration from 0 to x, it will be turned out to be 0 to 1 f of xy dy whole to the power p dx whole to the power 1 by p. So now you apply Minkowski's integral inequality. Minkowski's integral inequality. So if you apply the Minkowski's integral inequality, so integration will be changed from, so first one will be from 0 to infinity, and then it will be 0 to 1, and then 0 to infinity. And then integration of this thing, first of all, fx to the fxy to the power p will be there, then whole to the power 1 by p, and then dy, and then 1 by p. Whole is 1 by p is there, so it's there. Okay, so now again we got this by Minkowski integral inequality. Now again you just make a change of variable here, z equals to x into y. You just make a change of variable. So if you put z equals to x into y, you will get 0 to 1, 0 to infinity, fz to the power p dz, and you will get 1 by y to the power p, y to the power 1 minus 1 by p dy whole to the power 1 by p. So now you see this is a function of z and this is y. So you just integrate with respect to y. You will get p by p minus 1, and then it is as it is. So now you replace 1 by p both side. It is 1 by p. It's also 1 by p. So if you just multiply by, take the pth power, you will get this inequality. 0 to infinity 1 by x 0 to x ft dt whole to the power p dx is less equals to p by p minus 1 whole to the power p 0 to infinity fx to the power p dx, and this is true for p strictly greater than 1. Okay, so now what I'm saying, you just let fx equals to 0 to x ft dt. Okay. So if you if you take fx equals to this, so then what is f prime x? F prime x is nothing but fx. Okay. So now if you apply it here, this f prime x equals to fx and fx equals to this 0 to x ft dt, what you will get, this side is fx to the power p, so that means it is f prime x to the power p. So, okay, so you see f prime x to the power p dx 0 to infinity, this side it is greater equals to, and make this side p by p minus 1 on the left side, so it will come to p minus 1 by p to the power p, and then 0 to infinity fx by x whole to the power p dx. So for p greater than 1 and less than infinity. So this is the form we are interested in. So this result, so you can think that this things is true for any functions compactly supported C infinity functions. Okay. So if you take capital F, any compactly supported C infinity function, then this inequality holds, that f prime x to the power p integration over 0 to infinity derivative is greater equals to some constant into 0 to infinity fx by x to the power p dx. P is greater than 1 and less than infinity. Now what's its analog on Rn? Okay, so let me just write it. I have written it analog in Rn here. So you start with f any compactly supported functions on Rn. So then I'm just writing analog. What will be this? Here you just take grad of f whole to the power p dx integration over Rn, that is greater equals to n minus p by p whole to the power p integration over Rn fx by mod x to the power p dx. Okay, and also this constant is here, it's sharp, n minus p by p whole to the power p is sharp, so that means you cannot get a bigger constant for which this inequality will hold. Okay, so this is the analog of this. So this is called Hardy inequality on Rn. Okay, so for any p greater than 1, but it is less than n. Okay, so actually we will be interested for p equals to 2 case, only for p equals to 2 case. So but for that, first of all, we just observe that grad f inner product grad f, if you take its inner product, L2 inner product or these things, so you will get, this side is L2 inner product, you will get minus of Laplacian on Rn f comma f its inner product. So this is the Laplacian of f is this. It's the usual Laplacian on Rn. So if you replace it for p equals to 2 in this case, so what you will get? So integration, instead of integration over Rn, grad of fx to the power p, in place of p you just put p equals to 2.
Anamika Dubey, please stop presenting. It's creating disturbance because speaker is already speaking and delivering the address. So please,
How to?
I request Dubey, please stop the presentation.
can you see my screen?
No.
Okay, so shall I?
Just wait, Bablu, can we just
Anamika Dubey, please stop sharing.
I think moderator can.
Yes,
yeah.
I have to.
Yeah. Please,
Okay,
sorry.
so then I have to share it again, I think.
Mm.
Yes.
Okay, just a minute.
I request everybody, please don't share, as someone is already sharing the things. Is it
Okay.
okay? Yeah.
It is here.
Yes.
Okay, so this is fine. So what I'm saying is that for this, sorry. So this is the analog of Rn. I am just talking about Rn for Hardy inequality. So in place of p equals to 2, if I put, it will be grad of f mod square integration over Rn, and that means that integration is from here. You will write that minus, I mean, Laplacian of Rn f inner product f. That thing is greater equals to n minus 2 by 2 whole square integration over Rn mod of fx square by x square dx. Okay, so this is we will call actually this is Hardy inequality, but for p equals to 2 case. Okay, and this is true for any n greater than 2. And again, this constant is, again, this is the sub constant. That means you won't get any bigger constant than n minus 2 by 2 whole square for which this inequality will hold. Okay, before going further, let me just give some outline of this proof, how it goes. Okay, so you consider two operator on CC infinity Rn minus 0. So one it S of fx, this is equals to x fx by Rn. So that means S is a map from CC infinity Rn minus singleton 0 to CC infinity Rn minus singleton 0. So S is this, and A of fx is just grad of fx, two operator. Then you see that for, if you take for any y in R, then it is S of fx plus y into a of fx mod square dx integration over r, and this is always strictly greater equals to 0 and greater equals to 0. Now if you break into, I mean, modulus into, I mean, parts, 3 parts, so you will get mod of fx square whole square plus y square integration mod of a of fx square plus 2y integration over rn s of fx dot a of fx dx. Okay, so now you just applying just integration by parts on Rn, you can easily observe that integration over Rn s of fx dot a of fx is nothing but minus n minus 2 by 2 integration over Rn mod of fx square dx. Now you put this observation here. If you put this observation here, what you will get is that, so y square term is here, y square mod of a of fx square dx is there, and rest this term and this term you just combine together, you will get 1 minus n minus 2 into y integration over rn mod of fx square dx is get equals to 0. Now you observe that for any y this inequality holds. For any y this inequality hold. Okay, so now what we will do is that for the left hand side, so this part I will just observe, so this thing is true for any y, so we just find for which y this gives you minimum. So we find that if you just do the derivative once, you will get optimum point, and 2 times you will get that, oh, for y equals to this, if y is this, then this left hand side is minimum. Now you put y on the left hand side, you will get this your recorded inequality. So it's just so simple. So this is the Hardy inequality on Rn. Of course, we are everything we are in for p equals to 2, but we will fix p equals to 2. So this is the form that minus Laplacian inner product minus Laplacian f comma f, that is get equals to n minus 2 by 2 square integration over Rn mod of f square by f square dx for n strictly greater than 2. But here we have not proved that it is optimum constant or extremum constant, but this is the inequality holds. Now actually what we are interested in so here you see this is the power of 1, okay, minus Laplacian to the power 1. So what happens if we replace this power 1 by some fraction? But before to defining that thing, but we just need to know that what's the meaning of the fractional power of Laplacian. Okay, So before that, so let me just define what is the fractional Laplacian. So you just fix sigma in 0 to 1. Then I'm just going to define fractional Laplacian minus Laplacian to the power sigma on Rn. What is that? So it's a pseudo differential operator, whatever these things. Actually, it is defined by its Fourier transform. First of all, you just observe that Fourier transform, I will come to the how it is defined. First, you just observe that Fourier transform of a function is defined by this, some constant, then fx into e to the power minus I x xi dxi, okay? So now, you just observe if we take Fourier transform of minus Laplacian times f at the point xi, what you will get? You will get xi square or mod xi square f at xi or script f xi. Okay. So you see how you will get this minus delta of f by Fourier inversion formula. Minus delta of f is nothing but mod xi square script f of f xi, sorry, e to the power I x xi dxi. So this is your minus delta of fx. Okay. So instead, so when we are talking about this fractional power of that, what we will do is that, so we will define fractional power of sigma applied to f. If we take its Fourier transform, you will get mod xi to the power 2 sigma. Instead of here mod xi square is there, so here we will put mod xi to the power 2 sigma. So that means if we apply the Fourier inversion formula, you see this, compare it from here and here, you see the fractional power of Laplacian, I mean minus delta to the power sigma f of x, it is just integration over Rn mod xi to the power 2 sigma script f xi e to the power I x xi dxi. Though here I have written it sigma between 0 to 1, but this definition is true for any sigma, whenever this sigma exists. You see, if we take sigma equals to 1, so this definition actually nothing but it gives you this earlier definition, okay, earlier way. So that's the natural way to define the fractional power of Laplacian through Fourier transform. So now there is another way, to express the fractional power of fractional Laplacian. So this is the integral representation by singular integral. So it is that, so minus Laplacian to the power sigma f of x, it is some constant into principal value, say PV integration over Rn fx minus fy by mod of x minus y to the power n plus 2 sigma dy. So what is this PV means? Actually, this means that so this is, I can write in sigma limit. So you see, if your y is equals to x, then we have a singularity. So that's, how we define that, limit epsilon tends to 0 in the usual sense. Okay, mod of x minus y, you just take it as greater than epsilon, then you just integrate fx minus fy divided by x minus y mod to the power 2 sigma dy. Okay, so this PV means that in this sense that you just integrate when mod of x minus y greater than epsilon and take the limit when epsilon goes to 0. That's the meaning of PV. So this fraction minus delta to the power sigma fx, we have defined it one way from Fourier transform, and the second way is that through its singular integral way. Okay, so this is the, these two way we can define actually. Okay, so these two are equivalent. Okay, so these two. Okay, anyway, just one comment is here. This definition is true for any sigma. Okay, but here this theorem, it is strictly, for this integral, when sigma is strictly greater than 0 to 1, we have this integral representation. I think for sigma equals to 1 also we have this same kind of integral representation. Okay, so this is the fractional power of Laplacian. Now let's state what is the, what is the fractional Hardy inequality on Rn. So this is the definite, the theorem. I am just going to state there are two versions. One is homogeneous and one is non-homogeneous. And what is homogeneous things? What is homogeneous fractional Hardy inequality? You just fix an s greater than 0 and less than minimum of 1 comma n by 2, and f is compactly supported functions c infinity, c infinity, and then minus Laplacian to the power Rn whole to the power s f and inner product f, that is get equals to some positive constant. Actually, this is optimum, and integration over Rn mod of fx square by mod x to the power 2s dx. So now you just compare it to usual our on non-fractional power. You see the same. Okay, Laplacian to the power f, I mean Laplacian, then apply to f, inner product with f is get equals to mod of f integration over Rn mod of fx square by mod x square. Now here, if we take its fractional power, you are getting also same thing. If you take s equals to 1, you see it will be just same way. But the proof is not at all in the same way. So I'll just come to how it comes. So first of all, another one observation is that this constant is sharp. That means you won't get any bigger constant for which this inequality will hold. But you won't get any function for which this equality will be achieved. There's no, function for which this equality will be achieved. So this is for homogeneous fractional Hardy inequality. Now let me come to another one, is the non-homogeneous fractional Hardy inequality. What is that? No, instead of here you see that this weight, it is homogeneous function mod x to the power 2s. So instead of that, you just fix a delta for any delta greater than 0. So you see minus Laplacian to the power s applied to f, inner product with f, it is getting close to some constant, but integration over Rn mod of fx square by delta square plus mod of x square whole to the power 2s dx gets to 0. First of all, we should observe that this thing is true for all delta gets to 0. So if we take in the second part, if we take limit delta tends to 0, you see this integration part, you will get this part. Okay, but what happens is that this delta is here. If you take delta tends to 0, this part will go to 0. So yeah, so it does not mean that from here you won't get these things. Okay, so it's looks like that if you take delta tends to 0, you should get this homogeneous part, but you won't get. So in fact there is no relation between this homogeneous and non-homogeneous. Okay, so so these two are the fractional Hardy inequality. So these are proved by Frank, Lieb, and Singer. I think it's 2009. I think, yeah, 2009. So so let me just I'll just first give an outline of the proof of just only one of the homogeneous fractional Hardy inequality. So what is that? So before that, okay, so I'm just giving the outline. You just consider heat kernel. GTX is this. This is the heat kernel on Rn. Okay, so this is the heat kernel on Rn. So that means if you take GT hat at a point xi, you will get minus T xi square. Okay. Or in fact, it is just this, that if you e to the power minus T, Laplacian f is f star GT. So once you have heat kernel, you just define another one function, gs, script gs at a point x.
Sanjay,
Yes.
this is a convolution product.
Yes, it's a convolution. Yeah.
That is so
yes.
one of the set is compact support, right?
Yes, yes. I have assumed that if it's compactly
yeah.
Everything you see, it's compactly supported. Though we don't need, we can go up to Sobolev space function, but here at least we have assumed that it's compactly supported, so that everything makes sense and all these things. Okay, so here this thing is convolution here. So this is the heat kernel. It's a solution of the heat. Any solution of the heat equation you can write as a convolution with heat kernel. So once you have heat kernel, you just define some function script gs at a point x. It is just 1 by mod gamma of minus s, and then 0 to infinity this gtx dt divided by t to the power s plus 1 dt. Now we have exact expression of gt, so you put it here, then you will get some exact expression mod x to the power 2s minus n. Now I have just I have broken the steps into few. Broken the proof into few steps. So in step 1, what we have the integral representation of Laplacian. Okay, so fractional power of Laplacian minus delta to the power s f of x dx is equals to pv. Actually, there is some constant, I just forgot, c into pv, and fx minus fy into script gs x minus y. Okay, so this constant won't come here because, sorry, because we have constant here. So what is gs x minus y? It is mod of x minus y to the power n plus 2s. Already I have I told it that fractional Laplacian has an integral representation like this. Okay, fx minus fy by mod of x minus y to the power n plus 2 sigma. So if you put it there, so it is obvious that we get this. That's minus delta to the power s fx is pv fx minus fy script gs x minus y dy. Now, so this is in PV sense, principal value sense. Now, if you take the inner product with the function f, so what you will get, it's just in the absolute sense, it is just this. So you just need to add and subtract something, interchange, and then add. You would get that minus delta to the power s fx dx is some constant, and integration over Rn mod of fx minus fy mod square divided by x minus y to the power n plus 2x dx dy. After that, you just define for some alpha between 0 to n by 2, g alpha is just this, e to the power minus x square by t. Actually, it's some hit kernel and then t to the power n minus alpha. So you will get mod x to the power 2 alpha minus n. So then you just consider another one function, Vx is fx into g alpha x inverse. So g alpha x, we have this. So you just consider Vx. So then this is the major step. This is that's why it actually it's called ground state representation. So it has a name, ground state representation. So what is that? So minus Laplacian to the power s f minus some constant, then integration over Rn mod of fx square by mod x to the power 2s ds is some constant again, then integration over Rn, then you see Vx minus Vy square, so Vx is something, minus Vy by x minus y to the power n plus 2x, then g alpha x, g alpha y dx dy. G alpha x is this, so g alpha x into g alpha is this. Now you observe, so this things is the crucial step. So once you prove these things, then we are done, in a sense that you see that this right hand side of this equality is non-negative. This is non-negative, this is non-negative, all of this is non-negative. So it is getting to 0, and therefore you would get that minus Laplacian to the power s if inner product f is getting to that constant, integration over Rn mod of fx square by mod x to the power 2s dx. Okay, so this proves this Hardy inequality for, I mean, homogeneous Hardy inequality. But this constant is sharp, and for this we just need some other technique, and so I am not going to that. Okay, so now let me just come to the what's the story behind that and what happened so far. So first of all, what I have proved this fractional Hardy inequality, I mean, some version of that was proved by Beckner in 1995. And then this result is improved by this Frank, Lieb, and Seringer in 2008. So that's what that result I have just presented. This is the idea, and by Frank, Lieb, and Seringer. Then in 2009, this Kambe and Ujayedin, they proved for non-fractional Hardy inequality. So they have not considered Hardy inequality, only non-fractional Hardy inequality, but they have proved it for general Riemannian manifold. Okay. So again in 2015, CRT, Cowling, and Ricci, they proved fractional Hardy inequality, but it's for stratified Lie groups, but without subconstant. And then in 2016, Runkel and Thangavelu proved this Hardy inequality is the fractional power of sub-Laplacian on Heisenberg group. But again, they have proved it for with subconstant. Here it was without subconstant, but here it is for with subconstant. But here it is for Heisenberg group, and it is for stratified Lie group, and the Heisenberg group is some part of the stratified Lie group. Okay, so that was done, and our aim is to prove this this inequality, the fractional Laplacian, fractional Laplace Beltrami operator. You just take fractional Laplace Beltrami operator and then try to prove this Hardy inequality for this case for Riemannian symmetric spaces of non-compact type. Here also we did not get sub-constant, it's without sub-constant. Okay, so before going to do this, let me just little bit give the preliminary things. So I am not going to in any general case, but for the moment, you just have G is a non-compact connected semi-simply group with finite center and K is a fixed maximal compact subgroup. So instead of that, I'm just going to an example. You just take G equals to SL2R. That's 2 by 2 real matrix with determinant 1 and K is SO2. Okay, so I mean orthogonal matrices, special orthogonal matrices. Then you consider this symmetric space X equals to G by K. Then it is just your upper half plane. Upper half plane XY is Y greater than 0. But with the metric is that this is different metric than usual metric. DS2 is dx square plus du square by y square. Okay, so on this, with respect to this metric, the Laplace Beltrami operator on the upper half plane turns out to be this. Delta of f of xy is y square del 2 del x2 plus del 2 del y to f. In usual R2, it is just del 2 del x2 plus del 2 del y2, but with respect to this metric, this Laplace Beltrami operator is this. And this is a particular example of rank 1 symmetric spaces. So I am not going to the further, I mean in general cases. So now we have ISOR decomposition. That means this G you can break into 3 subgroup. K is SO2, so G is suppose SL2R. So you can write SL2R into 3 part, SO2, K, and A is your this metric, I mean this collections of matrices A, and then N is this. 1 j 0 1 this. So you can write ISOR that any element in G into 3 part. One is compact, so this part is abelian and this part is nilpotent. So that means if you take any element in G, you can break into one part in K, that means SO2, and this part X. So A part it's a group, but it has a Lie algebra script A. So you can write exponential of h of G and then NG. NG is in N. So this Hg is crucial for us. For using that Hg, we just define some object e to the power e lambda kg is something e to the power I lambda plus rho h part of G inverse of K. So H we have defined. So if you take G is in G, then H part of G is in A. So that means you can think of it as in R. So then it satisfies that if you apply Laplacian to E lambda K, you will get it will be an eigenfunction. So now you just compare with usual Laplacian. Usual Laplacian, and if you take e to the power I lambda x, so you will get minus lambda square e to the power I lambda x. Okay. So this E lambda K is something analog of e to the power lambda x. Okay, so using that, you just define the Fourier transform. Fourier transform of a function f is just given by fg, and then this is the E lambda k. Okay, so this is nothing but lambda k. So you see, when we define in general Fourier transform, f at lambda is integration fx e to the power minus I lambda x dx. So e to the power I lambda x is the eigenfunction. So here also the same thing. E lambda k is the eigenfunction of the Laplacian. So this is the Fourier transform on the symmetric space f tilde lambda k. For each lambda in R, you can think A star is in R and k is in k. And once you have this Fourier transform, you can write, what is the Plancherel theorem and what is the Fourier inversion formula. You see, Plancherel theorem is that L2 norm square is mod of f tilde lambda k square mod of c lambda to the power minus 2 d lambda dk, and this c lambda is Harish-Chandra C function. And if you take any L1 function and which f tilde is in L1, then inversion formula also holds the same way as in Euclidean case, but with a measure, with a weight, with a measure mod c lambda to the power minus 2. So actually, what is this C lambda? You can write it precisely in the upper half plane. C lambda will turn out to be this 1 by this. And for the rank 1 case, C lambda will be something, some gamma function by gamma function. Okay, so once we are in this case, we are, so, okay, so far what we have done, so let me just a little bit recall. We are in a symmetric space. So it's any symmetric space you can write into some semi-simple Lie group, non-compact connected semi-simple Lie group quotiented by a compact, maximal compact subgroup. So one example is that upper half plane, and there you have a Laplacian. And once you have a Laplacian and Fourier transform, you can define its fractional power of Laplacian. Okay, so once you have this fractional power of Laplacian, we can ask the similar question for the symmetric spaces. And what is that? That's what our result. So it's, again, here we have both the case, homogeneous and non-homogeneous. So you just take sigma is greater than 0 less than 1 and fix y is greater than 0. So then it says that if you take minus Laplacian to the power sigma f, inner product with f, you would get some c sigma y to the power 2 sigma, and then mod of fx square by y square plus mod x to the power 2 sigma dx. And for what is the for homogeneous weight, if you take sigma is greater than 0 less than 1, then again you will get minus delta. Delta means Laplace Beltrami operator to the power sigma aff is getting to some constant c prime mod of fx square by mod x to the power 2 sigma dx. Okay, so again you see that this Laplace fractional Laplacian with inner product is always get equals to something mod of fx square by mod x to the power 2 sigma. One is non-homogeneous case and it is homogeneous case. So now let me just go quick on outline of this proof. So here, if you remember this proof for the Euclidean case, so we have taken first hit kernel on the R, but now we will take hit kernel on X, HT. Then we defined two functions, Py sigma and P0 sigma, something by this. Hit kernel, then you multiply by e to the power minus y square by 40, then dt by t to the power y plus sigma plus 1 dt. So this is Py sigma and P0 sigma. And so once you have that, then we just get an integral representation of minus Laplacian to the power sigma fx, some integral representation through this. And so mind that here we got this integral representation for sigma greater than 0 and less than half. Okay, but only for rank 1 case we got for sigma 0 to 1 in the PV sense. But ultimately, for sigma greater than 0 less than 1, we could prove minus delta to the power sigma f inner product f is just like this, integration over x mod of fz minus fx square p0 sigma z inverse x dz dx. Now we define another one function g sigma x fx into py minus sigma x inverse. Then we prove something like in the Euclidean case, something like this ground state representation. Minus delta to the power sigma f 4 to the power sigma gamma sigma by y to the power 2 sigma gamma minus sigma integration over fx mod of fx square py sigma x divided by py minus sigma x dx is equals to something like this. So what is in the right hand side, again you observe that right hand side is non-negative. So you will get mod of f minus sigma square, sorry, minus delta to the power s f inner product is getting to some constant into mod of fx square py sigma x by py minus sigma x. So now what we do is that we get an estimate of py sigma and py minus sigma. We prove that this is getting equals to something like this, that x square plus y square to the power minus sigma if it is greater than 1, and mod of x square plus y square to the minus 2 sigma if it is less than 1. So if you put it everything here, we would get this non-homogeneous fractional Hardy inequality. So, and this proof of this homogeneous Hardy inequality more or less similar, and I think I should stop it here. There is something, some extension operator, but I don't want to go to this. So there are a few bibliography of this, these things. So it's, these things is proved for, I mean, fractional Hardy inequality, but for some cases, I mean, when the operator is some square of its vector field, and then this part, these things is for stratified Lie group, and This is our paper, still in archive. And this is the paper I just talked. This for fractional power of Heisenberg group. And that's all. Okay. So that's all. I think I should stop it here.
So any query from the audience?
I have one inquiry. Where you will apply this fractional power?
I think, yeah, this fractional power itself has lots of applications. I mean, when somebody study this, what is called geostatic equation or geostatic equations, there are lots of applications. I mean, these are to prove that existence of these solutions and all these things. Yeah. Specifically, what I know is that at least for geostatic equation, there's lots of studies going on.
Any other question? Then any other from the audience? Any query? No. So Sanjay,
Yes, sir.
I can discuss with you something.
Okay.
Okay. So Laplacian is on the Euclidean space, right?
Yes.
Laplacian Beltrami is a
Laplace-Beltrami.
generalization of Laplacian, right?
Yes, yes, sir.
Yeah, but it is on the Riemannian manifold. You can generalize
Yes.
on the but compact Riemannian manifold.
No,
right?
no, non-compact. What I said is the non-compact Riemannian manifold, but on any Riemannian manifold there is
your discussion is non-compact.
Non-compact, yes.
Yeah, I know that, but it is not. But as it is a divergency of the gradient, that
Yes.
Laplace transform, divergency of the gradient.
Yes.
So I think it is a linear operator.
Yes, it's a linear operator.
And it's positive.
Yes. And minus Laplacian is positive, not Laplacian.
Yeah, minus. So you are discussed all this inequality on the fractional inequality.
Yes.
On the hard about the hard inequality.
Yes, yes.
But it has been discussed in the Hardy space also.
In the Hardy space means you have taken the function on the Hardy space?
Yeah.
Actually, what I say is that here, though I have taken here compactly separated functions, you can take this kind of functions from the Sobolev space.
So yeah, Sobolev space, and somebody has done in the Hardy space also. I can discuss my friend.
Maybe in the Euclidean. In the Euclidean case, is it you said?
No, not only. Yeah, it is not only Euclidean, but I think he has something in Sobolev space. And he also generalized another one, my friend Pankaj Jain, and his school has done a lot of work on Hardy's inequality, Hardy space, littlehood Hardy inequality, and so many things.
Okay.
So your intention is only for non-compact and the fraction.
Yes. Fractional is actually when you apply this, when you do this fractional, all the machinery for the non-fractional way will not work. So something.
But you are taking but it is not. You are taking the s as a fraction. That is the.
Yes.
But you are not taking the integration as a fractional integral. But your integration is always our known integral, right?
Yes, that's the thing. I mean, so yeah, so that's the way. I mean,
that's the way. No fractional integral will not come into play.
No, here just our denominator is just fractional. That's all.
Only fraction, but there are somebody applying the fractional calculus. I am talking about that one.
Okay, no, I am not aware of that.
Oh, you are not aware. Thanks a lot. Very nice presentation from the beginning, from a very elementary stage about the Hardy inequality, Minkowski inequality, or in LP space or any other space. He also developed everything in very lucid way. So very nice presentation, Sanjay. Thanks a lot.
Thank you.
Thanks a lot. Now I hand over to Kaushik Ghosh.
So I am just leaving. Okay.
Now, Kaushik, is there anything, Kaushik?
Yes, sir. No, it's okay.
I hand over to the
yes.
session.
Okay. So thank you very much, sir, and thank you to Professor Sanjay Pushti also for his very wonderful talk, I should say. And
So
sure.
I should now stop my presentation, and shall I? So I'll leave it now.
So it's
Yeah,
okay.
you have a class, or you can leave
That
it.
is your
Okay.
choice.
Yes.
Okay.
See you again, Sanjay. See you again.
Okay, sir. I'll talk to you. I'll call you.
Okay. Thanks a lot.
Thank you very much.
Yeah. Bye.
So with this note, let us close this first session of this invited talk. And after that, we are having 3 parallel sessions of contributed paper presentation. So we are having session 2A, which will be chaired by Professor Gopal Sheet. Session 2B, which will be chaired by Dr. Gokul Shaha, and session 2C will be chaired by Dr. Krishnapada Das. So I request them to join accordingly, and all the participants who are having the presentation as well as interest to go through this particular presentation, please join accordingly. So thank you very much. I am also trying to share this particular links over the chat box. Those who are in session 2A, they will of course stay here. And I'm also trying to share these things. I think that is available now. This is the link for session 2B, as we know, already shared. And this is for session 2C. So thank you very much. We will have this parallel sessions now. And after that, we will join once again at around 6 p.m. because we are having 2 different invited talks. And then again, we will be having 3 parallel sessions. So thank you very much. We will join shortly here also. Thank you.
প্রফেসর রায়চৌধুরী, প্রফেসর রাজকুমার রায়চৌধুরী শুনছেন? প্রফেসর রাজকুমার রায়চৌধুরী, ওনার ফোনটাই ঝাম। প্রফেসর রায়চৌধুরী শুনছেন? শোনা যাচ্ছে না। জয়েনটা করেছে অথচ বাবলু
Sir, bolun.
Rajkumar Raichaudhuri has joined or not?
Let me check.
His photo is over there.
Yes, he is there.
But he cannot hear the
He's
mute করা আছে না বাবলু?
He's muted actually. I don't know.
This is for the pure session or applied session is mixed one, Bablu?
It is pure.
It is pure, right. প্রফেসর রায়চৌধুরী,
হ্যাঁ বলুন।
আপনার কি দাঁত অপারেশন হয়ে গেছে?
না হয়নি, এখনো ওষুধ খাচ্ছি।
কবে করবে?
21 তারিখ ডেট দিয়েছে, সোমবার কার্ডিওলজিস্টের কাছে যাব।
কার্ডিওলজিস্টে পাঠিয়ে দিয়েছে? বাবা,
কার্ডিওলজিস্টের পারমিশন না নিলে তো করবে না।
তাই নাকি? না, কমপ্লিকেটেড। কার্ডিওলজিস্টের কাছে পাঠিয়েছে এই শুনলাম। এমনি ওষুধ খেয়ে ভালো আছেন? এমনি ভালো আছেন?
এমনি ভালো আছি, চোখে ওই এই টাইপ করতে একটু অসুবিধা হয়, একটুখানি টাইপোস বেশি হয়ে যায়, সেটা ডান চোখের জন্যই মেনলি হচ্ছে।
দেখা ডান চোখটা অপারেশন হয়ে গেলে আশা করি কমপ্লিটলি নরমাল হয়ে যাবো আর কি।
হ্যাঁ, সেটা নিশ্চয়ই
বাঁ চোখটা হয়ে গেছে, বাঁ চোখটা হয়ে গেছে, বাঁ চোখটা হয়ে গেছে, কিন্তু ওই ডান চোখ দিয়ে দেখতে হচ্ছে তো, দুটো চোখের কম্বাইন্ড এফেক্টে একটু ঝাপসা দেখাচ্ছে।
তাহলে পাওয়ারটা দিতে পারবে না, তাহলে
হ্যাঁ,
পাওয়ারটা
এখন যে পাওয়ারটা দিয়েছে টেন্টেটিভ, ওটা অপারেশন করার পর আলাদা পাওয়ার দেবে।
হ্যাঁ, রাইট। এখন এটা দেখতে কোনো কষ্ট হচ্ছে না তো লেখাপড়াতে?
লেখাপড়াতে একটু কষ্ট হচ্ছে বই কি, একটু বেশি আলো না হলে দেখতে পাচ্ছি না, করে চলেছি। বেকার বসে থেকে কি করব, করছি, পেপার রিভিউ করতে হচ্ছে। এক সেকেন্ড, অ্যাপ্লাইড এর এটা লিংকটা কোথায়, এখানে আছে
না? আপনার অন্য লিংকে চলে যান।
আচ্ছা ঠিক আছে,
অন্য লিংকে চলে যান।
ওকে ঠিক আছে।
নাক বন্ধ থাকার জন্য আপনি ঘুমোতে পারছেন না, অক্সিজেন অক্সিফাস্ট রিলিফ স্প্রে, এটা বন্ধ না করা শুরু করে মাত্র 25 সেকেন্ডে। না সাহস হারাই, যা ভাবি করি সেটাই। সুতরাং লং লাস্টিং মেকআপ তাদের জন্য যারা সাহসী, যারা স্বাধীন। আমাকে দেখছে এতে নতুন চ্যানেল দিতে কি আছে? এতে আছে
I will request Dr. Gopal Chandra Sheikh to take the chair and start the session.
Today, my topic of okay, good evening, all of you. So this is yes, okay. So in this session, we have 7 participants. So each of them will take total 10 minutes. So for presentation 8 minutes and 2 minutes for discussion. So first I may request Mohammad Abdus Sahir. Please share your slide and present your work. He will be talking on A alpha spectra of graphs obtained by corona and edge corona operations and alpha cospectral graphs.
Can you hear me?
It's okay.
Okay. Thank you. Good afternoon, all. I am MD Abdul Sahir. I am now pursuing my PhD program under the supervision of MD Abu Naim sir in Ali University. Today, my topic of presentation is on A alpha spectra of graphs obtained by corona and edge corona operations and alpha cospectral graphs. Now, let me introduce. We all know what is graph, and the adjacency matrix of a graph is defined by A equal to ARS, where ARS is 1 whenever vertex VR and vertex VS are adjacent in G, and otherwise AR equal to 0. And the degree matrix of G denoted by DG is a diagonal matrix of which R diagonal entry is equal to the degree of vertex VR. the Laplacian matrix is defined by D minus A, and the signless Laplacian matrix is defined by D plus A. In 2017, Nikiforov has generalized the concept of adjacency matrix and signless Laplacian matrix by considering the convex combination of the degree matrix and the adjacency matrix. So he defined A alpha as alpha into D plus 1 minus alpha into A, where alpha belongs to closed interval 0 to 1, because this is a convex combination of degree matrix and alpha and adjacency matrix. Now we consider two graph operation. One is corona operation. Suppose G1 and G2 be two disjoint graphs with respective vertex set V1 and V2 and edge set E1 and E2, where the number of vertex in G1 is N1 and number of vertex in G2 is N2, and M1, M2 are the corresponding edges. The corona operation G1 circle G2 is defined by considering N1 copies of G2 and joining the ith vertex of G1 to every vertex of ith copy of G2. So the total vertices will be N1 into N2 plus 1, and total edge will be M1 plus N1 into M2 plus N2. And the edge corona operation between two graphs G1, G2 will be like this. The edge corona is denoted by G1 diamond G2 and defined by considering M1 copies of G2 and 1 copy of G1, then joining two n vertices of ith edge of G1 to every vertex in ith copy of G2, and the total vertex number of G1 diamond G2 will be like this, and total edge number will be like this. Now we are considering the adjacency matrix of corona operation G1 circle G2. The adjacency matrix of is G1 circle G2 will be like this, where this is the graph operation. Now the degree matrix will be like this, and the A alpha matrix corresponding to the corona operation of G1 G2 will be like this. Now coming to our theorem. Suppose G1 be any graph with n1 vertices and G2 be a regular graph with n2 vertices, and R2 being the degree of each vertex. R2 basically the regularity of G2, and also consider the A alpha spectrum of G1 is mu1, mu2, mu n1 with ascending order, and that of G2 will be delta 1, delta 2 and delta n2 arranged in ascending order. Then the A alpha spectrum of G1 corona product G2 will be like this. The eigenvalues will be delta j plus alpha, each with multiplicity n1 corresponding to every eigenvalue delta j, and lambda I bar will be like this, are two simple eigenvalues of G for each mu I. Let G1 be a graph on n vertices which is simple and connected, and G2 be another graph which is complete bipartite denoted by KAB, where M equal to A plus B, the vertex number, and also let that A alpha spectrum is known to us, and that is mu1, mu2, mu1 arranged in ascending order. Then the A alpha spectrum of G will be like this: alpha into A plus 1 as an eigenvalue with multiplicity n into B minus 1, and alpha into B plus 1 with multiplicity n into A minus 1, and remaining 3 n eigenvalues will be Pi Qi and Ri are equal to 1 2 dot 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 n, where Pi, Qi and Ri are the roots of this polynomial. Now, the corollary, let G1 be a regular graph with n1 vertices and regularity R1, and G2 also a regular graph with n2 vertices with regularity R2, and the adjacency spectrum of G1 and G2 are known to us. Not the alpha spectrum, only we need the adjacency spectrum, and the adjacency spectrum are in ascending order. Then we will have the complete alpha spectrum of G1 corona product G2. Now coming to the H corona product. Suppose G1 be a connected regular graph with n1 vertices and m1 edges and regularity R1, and G2 be another regular graph with n2 vertices and R2 being the regularity of each vertex. And also let the alpha spectrum of G1 is known to us like the previous case, and G2 is this. So we will have the complete alpha spectrum of G1 diamond G2, and this will be like this. And let G1 be a regular graph with n1 vertices, m1 edges and regularity R1. G2 be also a regular graph with n2 vertices and regularity R2, and the adjacency spectrum of G1 and G2 be like this: P1, P2, Pn1 and Q1, Q2, Qn2 in arranged in ascending order. So we will have the complete alpha spectrum of G1 diamond G2. Here we only need the spectrum of the adjacency spectrum, and we will have the complete alpha spectrum of G1 diamond G2. That means the H corona product G1 G2. Now the next theorem, let G1 be a simple connected regular graph with regularity R1 with n vertices and p edges, and G2 be a complete bipartite graph denoted by KAB, where m is the total number of vertices and q edges. And also let that alpha spectrum of G1 is known to us, that is mu1, mu2, mu_n, which will be equal, and mu_n will be the regularity of G1, and all the data is in ascending order. Then the alpha spectrum of G will be like this, that will be alpha into a plus 2 as an eigenvalue with multiplicity p into b minus 1, alpha into b plus 2 as an eigenvalue with multiplicity p into a minus 1, p, I, q, I, r, I are the roots of this polynomial in with multiplicity Pn, and alpha into m plus 4 plus minus alpha root under alpha square m square minus 4 into 2 alpha minus 1 ab by 2 as remaining eigenvalues of each of with multiplicity m minus n. Now we construct a class of cospectral graphs. We know from our theorem, if G1 and G2 are cospectral in the sense of alpha spectrum, and H be a graph which is complete graph or regular graph, then we can construct a class of alpha cospectral graphs of G1 corona product H and G2 corona product H. They will be alpha cospectral, and similarly we can construct G1 diamond H and G2 diamond H as a family of cospectral graphs, and these are the references here. Yes, sir.
Okay. So, any question from the audience? Okay, I think there is no question. Abdur, my question is, what is your conclusion from your work? Can you say in one line, 2 lines?
Yes, sir. In this paper, we have find the generalized version of uh, adjacency matrix and the degree matrix and their corresponding spectrum here, where we only need the spectrum of G1 and G2, and we will have the spectrum of their uh, convex combination.
Okay, so if there are no more questions, so you may unshare your slide.
Yes, thank you, sir.
So our next speaker, Jonabi Balaji.
Yes, sir.
He or she will be speaking on peristaltic transport of carrier nanofluid in the presence of triple diffusion in an asymmetric channel by multi-step differential transform method. Jonabi Balaji, please share your
Am I audible,
slide.
sir?
Yeah, audible. Show your slide.
Yes, sir. Is it my screen visible, sir?
Yeah, screen is visible.
Okay.
And if possible, please switch on your camera also.
Okay, sir. Now I can't, sir. Myself, Junabi Beleri, research scholar working under the guidance of Dr. S.K. Asha, Assistant Professor, PG Department of Mathematics, Karnataka University, Dharwad. The title of my paper is Peristaltic Transport of a Carrier Nanofluid in a Presence of Triple Diffusion in an Asymmetric Channel by Multi-Step Differential Transformation Method. Presentation outlines are abstract, introduction, mathematical modeling, results and discussion, conclusion, and references. Abstract. The current work is to deliberate the effect of triple diffusion on carrier nanofluid in a peristaltic movement through a symmetric channel. The governing equations are converted to standard nonlinear partial differential equations by using a suitable non-dimensional parameters. Solutions of emerging equations are found by using the multi-step differential transformation method. The role of influential factors on velocity, temperature, solutal concentration 1, solutal concentration 2, and solutal concentration are shown through the graphs. Introduction. Here, natural convection with the multi-diffusive properties has plenty of industrial uses. The triple diffusion motion appears in various scientific and engineering areas like astrophysics, disposals of nuclear waste, geology, chemical engineering, deoxyribonucleic acid, etc. It is a mixing process in which the density is determined by three stratifying agents with various diffusivities such as heat and salt concentration. When the thermal expansion coefficient and concentration of the elements in the mixture change significantly, the buoyancy force caused by mass transfer may have a significant impact on circulation of flow and component distribution in the cavity. The number of buoyancy forces increases as the number of components increases, and the behavior of the mixture becomes more complex as a result. The physical and mathematical conditions become significantly richer when the temperature and the two or more component agencies are combined. Further, Archana et al. Studied the influence of nonlinear thermal radiation and buoyancy force on triple diffusion flow considering the Kajna nanofluid model along a horizontal plate. Khan et al. Analyzed the influence of triple diffusion in a porous medium. Umawati et al. Investigated the convective flow of triple diffusion under Robin boundary conditions in a vertical flat plate. Namaz et al. Discussed the nanoparticles, double diffusion, and effect of diffusion thermal diffusion numerically. Peristaltic pumping mechanism embedded in a plenty of biological tools, including food intake through the esophagus, chyme flow in the gastrointestinal tract,
And
and
sorry for interrupting. Could you
okay, sir.
please directly go to your model and then explain?
Yes, sir.
Yeah.
My mathematical modeling here. The equation 1 represents the physical model of the asymmetric channel. Here, carry nanofluid peristaltic momentum propagating in a sinusoidal wave towards the channel's walls in a two-dimensional asymmetric channel as shown in a figure. This is the physical configuration where A1 and B1 denotes the amplitudes, D1 and D2 are the channel widths, lambda denotes the length of the wave, and C denotes the velocity propagation, and T is the time. Here, equation 3 represents the incompressible chorion nanofluid. The governing equations of the chorion nanofluid are from the equation 1 to 6 to 9. Equation C is the momentum equation, 8 is the velocity equation, equation 9 is the temperature, and equation 10 and 11 are the solutal 1 and solutal 2 equations, and equation 12 is the solutal uh, concentration of the nanoparticle. Now, equation 14 represents the non-dimensional quantities. By using the fundamental equations 6 to 10 can be reduced by using the above non-dimensional variables as shown in equation 19 to 24. Here, from removing the pressure from the equation 19 to 20, we will get the equation 25. And equation 26 represents the dimensionless boundary constraints. By using the multi-step differential transformation method, we will from in equation 19 to 25, we will get the following equations. Next, the transform form of the boundary conditions is also shown in the equation number 42. And we'll get the series solution as shown in equation number 43, 44, 45, 46, and 47. Differentiating the equation 42 partially with respect to the y, we get the velocity equation as shown in equation number 48. And by using the boundary conditions of the equation 26, we can obtain the values of the constants m1, m2, m3, m4, m5, and m6. Here, the system of nonlinear coupled partial differential equations is obtained from the above description. Exact solutions are difficult to achieve when solving explicitly. The problem in hand is approximated semi-analytically using multi-step differential transformation method. With the Mathematica software and graphical results are drawn in Origin software. Here, we discuss the development of velocity, temperature, solutal concentration 1, solutal concentration 2, and solutal concentration of the nanofluid. Corresponding to the variation of Weisenberg number, power law index, buoyancy ratio parameters NC1 and NC2, modified Duffer parameters ND1 and NT2, Duffer solutal Lewis number LD1 and LD2, Brinkmann number, and thermal Grashof number and solutal Grashof numbers, Brownian motion parameter, as well as thermoporesis parameter. In a figure 2, we can observe that velocity distribution for various values of Weisenberg number. As the Weisenberg number increases, the velocity distribution decreases. Similar behavior can be observed in case of a power law index. Next, in the figure 4 and figure 5. From the figure 4 and figure 5, we can observe that the buoyancy ratio parameters of solute 1 and solute 2, it affects as the buoyancy ratio parameters increases, the velocity distribution is also increasing. From the figure 6 and 7, we can observe that this is as the temperature distribution is increases as ND1 as well as ND2 is also increasing. In case of LD1 and LD2, the effect of LD1 and LD2 is also similar in case of temperature distribution. In case of solutal concentration 1, as the LD1 increases, the solutal concentration 1 is also increases. Similar behavior can be observed in case of LD2 also. In case of solutal concentration 2, as we increase the LD1, the solutal concentration 2 is also increases. The similar behavior is also seen in case of LD2. In case of soluble concentration, the LD1 is also increases and LD2 as LD1 increases and LD2 increases, soluble concentration is also increasing. Here we study the influence of natural convection with a triple diffusion on a peristaltic transport of karyo nanofluid in an asymmetric channel under the assumption of long wavelength and low Reynolds number. It is also seen that velocity in a peristaltic pumping increases with an increasing buoyancy ratio of soluble concentration 1 and C1, buoyancy ratio of soluble concentration and C2 due to the buoyancy force which dominates within the boundary layer. Velocity is influenced by buoyancy ratio, which is the ratio of fluid density contributions by the two solids. It is noticed that temperature profile increases for the larger varying values of modified Duffer parameters ND1 and ND2. Thermal conductivity rises as the thermal diffusivity rises, leading to an increase in molecular vibrations and as a result of temperature rises. In case of soluble concentration 1, soluble concentration 2, and concentration of the nanoparticles in a peristaltic motion increases by enhancing the values of the four soluble Lewis parameters LD1 and LD2. As a result of increased mass diffusivity, these parameters show a significant increase in a soluble concentration 1, 2, and concentration of the nanoparticles. And these are the following references. Thank you.
Okay, thank you, Jonabi, for your nice presentation.
Thank you, sir.
If there are any questions from the audience, please ask her. No questions. Okay, Jonabi, what are LD1 and LD2? Physically, what does it mean?
Yes, sir.
LD1 and LD2, what are those?
LD1 and LD2 are the Duffer soluble Lewis parameters, sir.
Okay. So actually, what it does play in this problem?
These are the mass diffusivity parameters, sir.
Okay.
As this parameter increases, the soluble concentration is also increasing, sir.
Okay. Okay. Thank you, Jonabi.
Thank you, sir.
Thank you again for your nice presentation. So now you can stop your sharing slide.
Okay, sir. Thank you.
Our next speaker, Afaq Ahmed Rather. Please switch on your video and also present your slides. He will be talking on a new generalization of power Lindley distribution with applications in cancer data. Please share your slides. Hello. Ahmed Rathe, are you here? Ahmed? Okay, possibly he is not present here now. Okay, so we can move to our next speaker, S. Karuna Ram. Are you present here, S. Karuna Ram?
Yes, sir. Yes, sir. I'm present here, sir.
Okay. Please share your slides and also please switch on your camera also, and try to finish your presentation within 10 minutes. And she will be talking on mathematical epidemiology. Please
yes,
share your slides.
Yes, sir. Good evening to the panel members and the professor who has supported us, Dr. S. Vasundhara ma'am. I am Gnanapriya and my teammate Karunya Ram. We are the students from G. Narayanamma Institute of Technology and Sciences, Hyderabad. Today we're going to present our paper, which is Mathematical Epidemiology. In this paper, we develop a mathematical note for the spread and control of the coronavirus. And also we're going to prove that COVID cases can be controlled by isolation. Introduction. Epidemiology is the study of distribution and determinants of the health-related states and events in specified population. In this context, the use of mathematical models aims to unearth from a large-scale perspective. One of the primary aims of epidemic modeling is helping to understand the spread of diseases in host population both in time and space. Mathematical modeling and simulations are important decision tools that can be useful to control the human and animal diseases. One of the most fundamental quantities used by epidemiologists is reproductive number, that is R naught. For microparasites, it is defined as the expected number of secondary cases following the introduction of one infectious individual into a fully susceptible population. It is understood from here that R naught has a threshold value in the sense that a disease must have R naught greater than 1 to invade the host population. Otherwise, it disappears right after its introduction. Next, the history of epidemiology is the first model in mathematical epidemiology is the work of Daniel Bernal on inoculation against smallpox in 18th century. The basic causes of coronavirus. The virus is known as severe acute respiratory syndrome, coronavirus 2, SARS-CoV-2. The disease it causes is called coronavirus disease 2019, as it is detected in 2019 in Wuhan. In March 2020, the WHO declared the COVID-19 outbreak a pandemic. Public health groups, including the US Centers for Disease Control and Prevention and WHO, are monitoring the COVID-19 pandemic and posting updates on their websites. These groups have also issued recommendations for preventing and treating the virus that causes COVID-19. And now my teammate Karunya Ram gonna show mathematically how it is proven that COVID-19 can be reduced by isolations. Thank you. Yes. Thank you, Priya. Good evening, everyone. I am Karunya.
Hello.
Yes, sir. Hello.
Do you have any problem? You have unshare your slide?
Yes, sir. I'm unable to share my screen, sir. Just a moment, sir.
Okay. Please try again. Yes, Corona. Do you have any connection issues?
No, sir. Just a second.
Okay, you are trying. Okay.
Sir, is my screen visible? Hello? Hello?
Yes, ma, it is visible. Carry on.
Yes,
Yes,
visible.
okay.
Yeah, it is visible. Okay.
You can make it full screen also.
Yes, sir. I have made it full screen, sir.
Hit with. Okay, no problem. You can continue.
Good morning to everyone. Now I'm going to continue that how isolation can reduce the risk of spread of COVID-19 with the help of mathematical epidemiology theory. So here we can develop a mathematical model. We have developed a mathematical model. For that we have assumed these parameters, susceptibility population as S, exposed population as E, isolated population as Q, recovered population as R, rate of susceptibility population moving towards infected and exposed class B, rate of exposed population moving towards the infected one as gamma, alpha, rate of exposed people take outside and isolation is gamma, rate of isolated person recovered is theta, and rate of infected people added to the isolated individual as added to the isolation individual as sigma, and rate of natural death plus diseases is equals to mu. So in this work we have in order to formulate our mathematical model, we have divided the whole population, total population into 7 manual existing exclusive compartments on the basis of other diseases status, namely susceptibility, exposed, asymmetric infected, that is A of T, and symptomatic infected but not quarantined, that is I, and symptomatic and quarantined infected as Q, hospitalized and isolated infected as H, and recovered as T population. So at the time of T total population, all the 7 will be equal to the total population. So in the simple terms, the assumption of the mathematical formula equations are these. ds dt is equals to a mu s t and beta ns n t e power t plus I, and the equation for exposed class equation for the exposed class infected class, isolated class, and recovered class. Here the first 4 equations are independent of the recovered class, hence we are excluding without generality. Then the last equation for the RT, that is recovered class, and the modified system becomes as shown in the screen, that is ds by dt is equals to a minus mu st minus beta n into st plus into et plus it for all the and for the remaining also exposed class, infected class, and isolated class. For the system 2, that is the above equations, we assume that n is equal to a by mu, and s is equals to s by n, and e is equals to e by n, and I is equals to I by n, and rescale the system 2 to get a normalized form, that is which is nothing but the equation 4, 5, 3, 4, 5, and 6 for respectively susceptibility class, exposed class, infected class, and isolated class.
and the isolated class. So for this, to get an equation with, we use some initial conditions. That is, for the susceptibility class, S0 should be less than or equal to 0, and E0, and for the exposed class, E0 should be it should be less than or equal to 0, sorry, greater than or equal to 0, and I0 and I is equals to, and I0 should be greater than or equal to 0, and Q is equals to Q0 less greater than or equal to 0. So, and for this equation 7, all the solutions, that is susceptibility, exposed and infected, and also the isolated of the systematic of system 3 remain non-negative for t less than or equal to t less than 0. So here the proof of this above equation is the system 8. D by ds ds by dt is equals to mu greater than 0, and similarly for the exposed class, isolated class and infected class. Now when it comes to the local stability and existence of a positive equilibrium point, we consider here the result is observed for the positive and boundness of the solution for the system 3. So for that, we consider the following matrices for finding the basic reproductive number R0. Then we'll get an F and a V value. For that F and V value, we use in Jacobian. Then the dominant eigenvalue of FV inverse represents the R0. That is, R0 is equals to beta n into sigma plus mu plus pi by pi plus sigma plus gamma into sigma plus mu. Then for the system 3 is locally stable related to virus free equilibrium C0, and R0 less than 1, and unstable if R0 greater than 1. For that, the proof is, for the local variable stability at C0, the Jacobian system is this one. We'll get this one, the above equation which is on my screen, which is nothing but the eigenvalues for lambda 2 less than 0, lambda 3 less than 0, and lambda 4 less than 0. And if R0 is less than 0, so the system 3 is locally stable if R0 less than 0, and unstable if R0 greater than 0. And next, theorem 2, that is, there exists a unique positive virus equilibrium point, that is C0, for a system 3, which is in the condition if R0 greater than 1. For that, the proof is by letting the right hand sides of all the equations of the system 3 to zeros, as mu minus mu s minus beta ns into e plus I is equals to 0, and mu ns into e plus 1 minus pi e minus mu plus gamma into 0 is equal into e is equals to 0, and pi e minus sigma I minus mu I is equals to 0, and gamma e plus sigma I minus theta minus mu q is equals to 0, which is nothing but the susceptibility, exposed, isolated and infected classes, the result. So from the values of I star, it is obvious that all the values of C star, that is C star of S star and E, I and Q stars, are positive if R0 greater than 0. And the next theorem is theorem 4. If R0 less than 1, then the system 3 is globally stable. For that, the proof is the proof of this theorem here. So first, for this, we need to construct a Lyapunov function. That is equation 15. That is L is equals to E minus E0 plus beta n by sigma plus mu into I minus I0. So by differentiating the equation 15 with respect to time and keeping the reality in mind that r naught is less than 0 and 0 less than s less than 1, we get the equation that L dash is equals to E dash plus beta n by sigma plus mu into I dash, and L dash is equals to beta ns E plus beta ns minus 1 minus sig.
Can you
So,
go fast? Your time is already over.
Yes, sir.
Can you
So
please
we'll
show
get
your
the
one or
equation.
two important results and then directly go to conclusion?
Yes, sir. So we'll get the last equation. So therefore, we can say that if R naught less than 1 and L naught less than 0, which implies that the system of 3 is globally stable for R naught less than 1. And and here we use a numerical methods, that is numerical methods for obtaining a solution of our proposed model for the equation 3. So here the numerical method we are using is iterative method, in which we get closer to this solution through iteration method for the equation 9 and 10. So by solving the equation the equations, by solving that we get this one. Here with k is equals to 1 and 2, and then by NFD method we get the y dash n is equals to yn k plus n minus 1 yn comma k by h. Now by using NFD method for a numerical solution of system 3, it follows the equation as shown on my screen here for the susceptibility, isolated, infected and exposed classes. So, and the last thing is here we assume that the parameters of the system 3 as shown in the table 1, which is the starting one here. Now I request Priya to share the screen once again for the PPT. Hello.
Hello.
Yes, sir.
Did you finish your, or you will show your conclusion?
No, sir. Just a moment, sir. Just a moment.
Yes, sir. Kanya, can you please stop sharing your screen?
Yeah, sure.
Priya Reddy? Yeah.
Yes, sir. Is my screen visible?
No, please click on your slide.
Yes, sir.
You open your slide. Open.
After the results, from calculating the results from the equations, these are the graphs plotted by them.
No, your slides are not visible to us.
No, sir. 1 minute. Now, sir?
No. Okay, now it's coming. Yes.
Yes.
Please.
Thank you, Priya. So, when we observe the graph, which shows the solution for the susceptibility exposed, isolated, and infected, and also the recovered, obtained by an NSFD methods for R naught less than 1, which shows that it is unstable and will never become stable because of the contact rates of an infected people of susceptible people. So, according to the Act of Governments, if to keeping people within a specified bounds, that is maybe their homes or to stay at home and save their lives, or office, etc., whatever the place, the contact rate can be controlled, and so the current pandemic, otherwise no control is possible. For R naught, yeah, sure. Can you move to the next slide?
Yes, I have.
So the next one, next slide, which represents the R naught value less than 1. When the contact, which is nothing but the, which is when the contact rate becomes smaller, then the current infectious disease can be controlled. Yes. Priya, you can take over this.
Okay,
now.
tell us your conclusion.
Yes, sir.
Yes. So,
our model shows the coronavirus spreads through contact and describes how fast something changes by counting the number of people who are infected and the likelihood of new functions. So we have in this PPT we have shown that how we can control the COVID-19 by isolations. Yes, sir. And these are the references which we have used for doing our paper presentation. Yes, sir. Thank you.
Okay, your references are not visible. Anyway, but any questions from the audience, please? No. Okay, so because of the time restriction, so we can move to our previous speaker. I think now he is present. Afaq Ahmed Rathir, are you present now?
Yes,
Are you
sir.
here?
Yes, sir.
Afaq Rathir?
Yes, sir. Yes, sir. I am listening.
Okay. So
Can
please
I?
share your slides and also make your video on if possible.
Okay, okay.
Hmm. Please click on the button present now.
Yes, sir. Yes, sir. I am.
Okay.
There is some issue, sir. Can I present after one more candidate because there is some issue in my laptop? I am
Oh,
extremely
okay.
sorry for.
Okay, no problem. You
Okay.
ready with it? So we
Okay, okay.
can.
Because it. Yes, sir. Yes, sir.
Okay, we can move to next our speaker, Kopil Shankar Gaur.
Okay.
Are you ready, Kopil Shankar? Kapil Shankar Gaur. I think he is also not present now. Next speaker, Anamika Dubey. Are you here, Anamika?
Yes, sir. Present.
Okay, yeah. Please present your slide. Yes.
Yes, sir.
Okay, Anamika Dubey.
Yes.
He will be presenting
Yes, sir.
on a chain involving the function transform.
Yes, sir. Sir, screen visible?
Full screen or make it quite large. Is it possible to make it quite large? Full screen, you click on present slide. Yeah, now it is good. Yes, yes, yes. Okay, you
Thank you, sir.
carry on like this. Yes.
Good evening to all of you. My name is Anamika Dubey, guest faculty, Department of Mathematical Sciences, Avdesh Pratap Singh University, Riva. Today is my presenting paper on a chain involving the Aleph function transform. Contains introduction, main integrals, special cases, and references. Introduction. Throughout this work, we use the notation Aleph function of one variable. This equation 1.1 for the Aleph function transform defined by references to the kernel in 1.1 is the well-known Aleph function which is quite general in nature and includes most of the commonly used functions as its special cases. The definition of this Aleph function in terms of a Mellin-Barnes contour integral, various conditions satisfied by its parameters for the convergence of the defining integral, some of its special cases, important properties, and adjuncting expansions can be referred to in a standard work on the subject by references to main integrals, results 2.2 and this 2.3 equations, where capital N is a positive integer greater than 1, capital In is equal to this equation, and capital Jn is equal to this. It being assumed that the integrals involved in equation 2.1 and 2.2 are absolutely convergent and the following sets of conditions are satisfied. This equation, real number of these equations where capital An and capital A dash n is equal to values and the notation alpha jm suffix 1 m is equal to 1 to n stand for a sequence of this. And special cases, if in the main theorem we replace m suffix k by m suffix k plus 1, small pk by mk, qk by mk plus 1, nk by 0, and this equation, and take alpha jk is equal to beta jk is equal to 1, j is equal to 1 to that dash mk plus 1, k is equal to 1 to that dash n, b suffix mk plus 1, k is equal to pk. Therein it is reduced to the following results involving the g functions transform. This references 5. Corollary, if this equation 3.1, 3.2 and 3.3 where Pn and Qn and the conditions of validity directly obtainable from the main theorem are assumed to be satisfied. If in corollary first we take mk is equal to pk is equal to 0, k is equal to 1 to that dash capital N, it reduces to the following result involving the well-known Laplace transform. So if Laplace transform this equation 3.4 and 3.5 and 3.6 where capital Rn is equal to sigma I is equal to 1 to m minus 1 c1 plus m minus 1 m is equal to 1 to n, and the conditions of validity directly obtainable from the main theorem are assumed to be satisfied. This references and proofs are Mellin-Barnes contour integral, use of the proofs and the references first. And thank you.
Okay, thank you, Anamika Dube, for your nice presentation.
Yes, sir.
And if there is any question from the audience, please. No, I think there are no questions. Okay, thank you, Anamika.
Thank you, sir.
Okay, now you may unshare your slide.
Yes, sir. Thank you.
Okay. So now I am requesting Sonu Kumari. Are you here?
Yes, sir, I am here.
Okay. So please share your slide and present your work. She will be talking on the weight enumerator of generalized Reed-Molar codes. Please open your slide.
Ma'am, please stop your presentation.
Yeah, Anamika Dubey. Okay. Now, Sonu Kumari, please share your slide.
It is visible, sir?
No, please share your screen first. Please share your screen. Oh, it is not visible to us.
No, sir.
You go to
It is not work. It is not working.
No, Anamika Dubey, please do not share your slide. Only now Sonu Kumari, she will present her work only. Sonu Kumari, please share your slide. You first make your screen share. Yes, it is coming now. Good. Where is your slide, please?
Yeah, just wait.
Okay.
1 minute. It is visible?
Yes, make it full screen or make it larger. No. It is not possible to make it larger?
No, sir.
Okay, are you presenting from your mobile device? Mobile?
No, sir. Laptop.
Okay, so you have opened from which PPT or PDF? Which one is it?
Sir, PPT.
Okay, you see below, do you have any slide presentation option or go to
No, sir. It is not done.
Okay, so again you share your slide. Maybe you can continue with that. Please share your screen again. Yes. Yes, now it is coming. So now you go to your slide and then yes, it is now
Yes.
perfect. Okay.
Yes, sir.
Continue.
Good evening, everyone. This is Sonu. I am presenting my research work under the supervision of Dr. Shima Thakran in Department of Applied Science of the North Cap University, Gurugram. And there are the outlines of this presentation. First one is abstract, second is introduction, third is read-Muller code and generalized read-Muller codes, and then after weight enumerator, and then the weight enumerator of GRM codes of order m-3, and then after is references. And title of this research paper is the weight enumerator of GRM codes and of order m-3. And you can see there are the abstract of this. In this paper we have formulated and analyzed a specific account of weight enumerator of generalized read-Muller codes, and where m is lies between 3 to 4 and r is lies between 1 to 4, and also s is lies between 1 mc r plus 1. And there are the followings are keywords: way to Reed-Muller code, dual of Reed-Muller code, generator matrix, and generalized Reed-Muller code, and dual of generalized Reed-Muller codes, and weight numerator and puncture vector, and then after is McWilliam identity. An introduction: in 1948, Carl Shannon published a paper titled with A Mathematical Theory of Communication, and his main groundbreaking work was that when a message is sent to someone, it was received as the original form, and for that work using probability theory developed by Norbert Wiener. And in the coding theory, various code and their properties and their application, like uh, quick wit device, CD player, and are used. And the codes are mostly used for error correction, detection, data transmission, and data storage. And code are very useful in information theory, computer science, mathematical science, and many other fields. And we have some well-known codes in coding theory like PCH code, Hamming code, Hadamard code, cyclic code, and Reed-Muller codes. And this paper is in this paper we have work on Reed-Muller codes, and this is the definition of Reed-Muller codes. Reed-Muller code are well known binary codes, and for any positive integer r, and m r is less than m, there is an rm codes is the notation of Reed-Muller code of order r, formed by using as a basis of vector v1 not v1 v2 vm, and all vector products of v1 v2 vm taken or are fewer at a time, where these vectors are row of a matrix that has column which are binary representation of 0 1 and 2 raised to the power m minus 1, and the vector v naught has all its component are as 1, and the minimum distance of Reed-Muller codes of order r is equal to 2 raised to the power m minus r. And this is the iteration of Reed-Muller code of order 1. And next, Reed-Muller codes are generalized in many ways. And in 1981, Das and Mattu obtained a new class of generalized Reed-Muller codes known as Theorem code of order or MS, and by extending Reed-Muller code. And the dual of these codes are also studied by Das and Tyagi. In 1988, it has developed the order of dual of JRM codes of order m minus r minus 2 and mr1. And this is the definition of generalized Reed-Muller codes, and there are the illustration of generalized Reed-Muller codes, and simply known as ZRM code. And this is the continuation of definition of ZRM code. Weight enumerator. In very beginning of the coding theory, the distribution of weight enumerator of code has been a fascinating problem. The essential difficulty in coding theory with authorized weight distribution is existence and uniqueness of code. As coefficients in polynomial distribution of weight can be encoded called weight enumerator, where there is the illustration C. C is equal to a code word like that 1101100 is any code 1 in a binary code C, and the total number of non-zero entries like 1 in C is the weight of this code word C. This is notation WC is equal to 4. And continuation of a definition of weight enumerator, the distribution of weight enumerator gives the new idea to contract of the information about the code for finding the error probability of a code, and for other reason when a information sent from one place to another place across a noisy channel, the error might occur. Right enumerator help us the correcting error happen in noisy channel. And the weight distribution of an error correcting counts for every given parameter. The distribution of weight enumerator of a code is the main characteristic of the code, and the behavior of the codes from both theoretical as well particle aspects. And weight enumerator is applied to study the vast transformation of monomial function over the finite field. And this is the result of weight enumerator of GRM code of order m-3. Here hx be the weight enumerator of these codes, and the value of h lies between 0 and greatest integer m by 2. And idea of this paper we got from the research paper BK Das and Vashan in 1983 on code of order r plus 1 ms, and this is the weight enumerator of GRM codes of order m minus 2. Now we prove our result. Let fx, gx, hx are the polynomial of weight numerator, fx for Rm of order m minus 3, gx polynomial for dual of order m minus 3, and hx polynomial for jrm of order m minus 3 respectively. Since we know that the Reed-Muller codes of dual Rm is equal to Reed-Muller codes of order m minus r minus m, and for this we get Reed-Muller codes of dual m minus 3 is equal to Reed-Muller code of order 2. Then by using the Nell and Solon results on weight numerator of second order Reed-Muller codes, here Gx be the weight numerator of second order Reed-Muller codes, and the values of i's are denotes the number of code words of weight I in Reed-Muller codes of order 2. And these are the expression of AIs. And next, by using the Mac-Williams identity, we get the weight numerator of Reed-Muller codes of order m minus 3m, and this is the polynomial fx from we get from the help of polynomial gx. And you can see there are the generator matrix G, and which is the generator matrix of JRM codes of order m minus 3, and here the rows of the matrix X representing the product of S vector of V1, V2, Vm, and taken m minus r minus 1 at a time. And let X be the represent linear combination of rows of X, and the code JRM of order m minus 3 be the disjoint union of the consist of 2 raised to the power s minus 1 cosets, and v plus rm of order m minus 3 m, and code rm of order m minus 3 where v is r belongs to lx and v is not equal to 0 in lx. And let the weight numerator of a coset of coset v plus rm of order m minus 3 is denoted by ax where v r belongs to lx and v is not equal to 0. And using the Asmus and Madsen develop a result on weight numerator of coset of a linear code, and by using this result we get the polynomial ax. Here ai is denoted 2bi minus capital Bi's, where the number of code words of weight I in Reed-Muller codes of order m minus 3 dual is denoted by bi, and the number of code words in order Rm of order m minus 3 that are orthogonal to V is denoted by small bi's. And now the basis of the vector of in this are denoted by small bi's. And for this we will discuss the values of AIs as case number 1, taking r is equal to 0, m is equal to s, and s is equal to 1 to 4. And these AIs are found with the help of MATLAB and GAP software. And case number 2, we will take r is equal to 2, m is equal to 5, and s is equal to 1 to 7. And these are the values of AI. Next, case number 4, r is equal to 4, and m is equal to 7, s is equal to 1 to 19. And now put the all values of AIs in the polynomial AX. We get the polynomial AX, and which is the weight numerator of cosets. And after that, by using the polynomial fx, ax, and we get the polynomial hx, and hx be the result of weight numerator of GRM of code order m minus 3. And there are the illustration of this. These are the illustration. And these are the references which I have used in this paper. Thanks.
Okay, thank you, Sonu Kumari. Thank you for your nice presentation. So now, any questions from the participants or invited persons who are here? Please ask if you have any questions or queries. No. Shanu Kumari, I have one queries, may not be questions. Is
Yes,
there any
sir.
relation between code words and the polynomial AX?
Yes, sir.
Means if you increase the number of code words, then how it will affect the degree of the polynomial?
Yes, sir, they are increased.
But is there any relation? Means and if you increase your number of code words by 1, so then what should be the degree of this polynomial ax?
So it is depend on 2 raised to the power order of the polynomial.
Which polynomial?
Uh,
Means how much degree of the polynomial will increase if you increase one code word?
Sir, because JRM codes are the extending and shortening of Reed-Muller codes.
Okay.
And then polynomial degree are 2 raised to the power m.
2 to the power m.
Yes, sir.
Okay. So if your number of code words increase by 1, so polynomial should be increased by 2m plus 1 or 2m plus 2 or
No, sir.
any other.
Because we will take the vector v from generator matrix of JRM.
Okay.
So only not extended and not
Okay,
less.
okay, I see. Yeah, okay, understand. I see.
Yes, sir.
Oh. Okay, thank you, Sonu Kumari. Thank you for your nice presentation. So now we have one more participant, Mr. Ahmed Rathe. Are you ready now?
Sir, I'm ready. I am
Okay.
ready. I will try, sir. Actually, I think I have some once I am trying to present share this paper, but it is not coming on the screen. Can I present without that, sir? Because there is
Without
some issue.
slide, how we can understand?
Yes, sir.
It
Actually,
is
I
not
think
possible. It is. Can you
yes.
try once again? You just go to the present now. And
Sir, can I
share your
present,
screen.
sir? Okay, sir. I will present last. You go ahead, sir. I will try. I will. Okay, thank you. Sir.
No, this session is already over. Only you are the last person.
Sir, can I present, sir? There is some technical issue, so
Kapil Shankar.
yes, sir.
Speak loudly what you are saying.
Sir, there is some technical issue, so my network is not appropriate. So can I present?
Just what is your name, please?
Sir, Kapil Shankar God.
But it is not in this session, but I think it is in the next session.
No,
So,
sir.
Shankar, I think this is not at this particular session you are having your presentation.
Okay, sir.
So please be there at that time. Okay.
Sir, can I present then? Because it is
yes,
not.
yes, okay. You
Sir,
present.
sir,
Okay.
but one issue is once I am trying to share the document, it is not actually there is not coming. I think in my laptop there is some issue. Can I
Okay.
present?
So
Sir?
you can tell us what is actually
Okay, sir. Okay,
overview
thank you.
of your work and then
Yes,
tell us
sir.
the result. But at the
Okay.
end, you should send your slide to us. To us.
Okay, sir. I will send mail also, sir. Okay.
Okay.
Thank you, sir.
And if
Thank you.
possible, you can also share now. If it
Okay,
is
sir.
possible.
Okay, sir. It is not coming. I think some problem maybe in my laptop, sir.
Okay. Okay.
That
You
is
state your problem and
okay.
discuss what you have done. And
Okay,
at
sir.
the end, you must send your slide to us. Okay.
Okay, sir. Okay, thank you, sir.
Okay. Please.
Okay, good
Please
evening to
finish
all of.
within 10 minutes. Yes.
Okay, sir. Good evening to all of you. I am Dr. Afaq from Government Degree College, Udi, Kashmir. Today I will present my paper. The paper title is A New Generalization of Power Linearly Distribution with Applications in Cancer Data. The introduction about this title is the concept of weighted distribution is traceable to the work of Fisher. This idea was given by R.A. Fisher in 1934. The weighted distribution reduces to the length biased distribution when the weight function considers only the length of the units. The concept of the length biased sampling was first introduced by Cox and Zelen. The Erlang truncated distribution was originally introduced by Erlang et al. 2007, which is an extension of one parametric exponential distribution. Here in this paper, we are making the weighted Erlang truncated exponential distribution, this weighted model. The PDF of the Erlang truncated distribution is given by equation first, but unfortunately you can't see. And the CDF is in equation second. After this, we are making the weighted model of this weighted model is f of x is equal to wx fx.
No, you should read at least one PD, what equation you have taken. Yes.
Sorry. Actually, sir, I have taken PDF of Erlang truncated exponential distribution. That is the base distribution, which I made the weighted model, sir. Okay. Erlang truncated exponential distribution, that is the base distribution. We have making an extension, namely weighted Erlang truncated exponential distribution. The weighted model is fx, which is equal to wx into fx. Fx is the PDF of base distribution divided by its mean, where wx is the weight function, which is a non-negative function. After making simplifying it, and we have calculated its PDF, and similarly we have calculated CDF. And in graph first and graph second, which is the weighted Erlang truncated distribution, which shows the various several values of parameters as seen in figure first and figure second, but later I will see that, sir, those slides. In figure third and four, which shows the way the survival rate and hazard rate function of the weighted Erlang truncated distribution. After that, we have estimated the order statistics, where we take first let x1, x2, xn be the order statistics of a random sample drawn from the continuous population with probability density function, and it is CDF, cumulative density function. Then the PDF of rth order statistics, which is mentioned here, and from that rth order statistics, that PDF, we can similarly estimate the first order statistics by putting r is equal to 1. We can estimate the second order statistics by putting r is equal to 2. Similarly, so on and so forth. Just to, we can calculate.
Anamika Dubey, please unshare your screen.
Sorry, sir.
No, not you. Anamika Dubey, please stop your sharing. Yes, continue.
Okay, sir. After order statistics, we can estimate the unknown parameters by maximum likelihood estimator. This distribution is a 3-parametric distribution, where we are taking first a PDF, and after PDF we are making it its likelihood function. After making it its likelihood function, we are using the log on both sides. While taking log, we are estimating then parameters. This is 3-parametric distribution, beta, alpha, and c. Sometimes it is becoming very complicated to estimate the parameters. Then we are using our software to estimate these unknown parameters, which are here beta, lambda, and c. This is a 3-parametric distribution. After estimating parameters, we are going the next step, that is the application part, which is the one of the most important part. In this paper, we have used the cancer data. This is the 120 patients of a cancer, which is taken by Rams et al. 2013. And second data is Grass and Clark 1975. This data was Lily of 20 patients, which is also mentioned in this here. And from that, we have taken this data and we have compared our distribution weighted Erlang truncated distribution with 5 basic distributions, in which one of the distribution is famous exponential distribution, power Lindley distribution, Erlang truncated distribution. We have compared this data, we have calculated, we have used this data in our software, and we have estimated the parameters. We have estimated -2 log L, AIC, BIC, and AICC. In this way, the lesser the values of AIC, BIC, AICC, the better the performance of the distribution. If we see in data, our distribution is these values are all less, so we can say our distribution performance better than the other distributions. Here we have also shown in graphical method in graph, where we have used our software for this. We shows the fitting of density curves of 2 data sets as shown in fig of weighted Erlang truncated distribution, which shows that it is more flexible than the other distributions. Thank you, sir. Thank you.
Okay, thank you. So we have tried to understand what you have did. Okay, anyway, but you have to send your slide.
Yes, sure, sir. I will send now. I am extremely sorry, sir. I don't know what happened this, unfortunately.
Okay, thank you. Okay.
Okay.
Any question from the participants and distinguished person here? No. So I think there is no question. So thank you again, Rathir.
Thank you, sir. Thank you. Welcome, sir.
So I think this session is over. So now I'm switch over to Dr. Kaushik Ghosh, please.
Thank you. Thank you very much, Dr. Sheet, and for your
Okay.
very wonderful cooperation. And we are quickly moving on to the different invited talks. We are having now 2 consecutive talks. This will be our 5th invited talk, and then it will be followed by the 6th one. The first one today, it will be delivered by now Professor Ananda Shankar Chaudhary. He's from Jadavpur University, Kolkata. And the title of his talk will be A Mathematical Journey in Computer Vision. And this session will be chaired by Professor Joydeep Chattopadhyay. He's one of the vice presidents of our Calcutta Mathematical Society. So I request Professor Chattopadhyay to kindly conduct the session.
Thank you, Kaushik. So, good evening, ladies and gentlemen. It's my pleasure to introduce Professor Ananda Shankar Chaudhary. Professor Ananda Shankar Chaudhary is a professor and head of the Department of Electronics and Telecommunication Engineering at Jadavpur University. He received his PhD in computer science from the University of Georgia, USA in 2007. He did his postdoc in the Department of Radiology and Imaging Sciences at the NIOH, USA, during the period August 2007 to December 2008. His area of research interest is vast. He is mainly working on computer vision, pattern recognition, biomedical image and signal processing, and multimedia analysis. Professor Chaudhary has published quite a good number of research articles in well-reputed journals. He visited several countries, academic visit, of course. I will mentioning some of them. He visited University of Münster in Germany, National University of Singapore, University of Campinas, and University of Sao Paulo, both in Brazil. And he is a senior member of IEEE. He currently serves as an area editor of pattern recognition letters, a senior area editor of IEEE signal processing letters, and also an associate editor of Spin and Nature of Computer Science. So with this short background, may I request Professor Chaudhary to start your lecture, please. Thank you.
So thank you. Am I audible?
Yes, yes, yes.
Okay. Thank you, Professor Chattopadhyay, for your kind introduction, and my heartfelt thanks goes to my old friend and collaborator, like Professor Kaushik Ghosh, for giving me an opportunity to talk before this esteemed audience regarding like what we do in our group. So let me share my screen. So is the screen visible?
Yes.
Okay.
Yes, it is visible.
Thank you. Okay, so the title of my talk is A Mathematical Journey in Computer Vision. So over next 40 minutes or so, I will take you through, some, let's say, a tour in computer vision. Like, well, 40 minutes probably is, just like I have to sample some, and I will focus on 2 very different applications. But indeed, like computer vision is a very fascinating area of research where concepts from different domains are pouring in. So we have like a small group. I have formed like a small group at Jadavpur University in our department, and we have termed our group Imaging Vision and Pattern Recognition. So I will, as I have mentioned, like I will mainly focus on like 2 different problems. One is computer vision for healthcare, and I mean the domain, and the domain for the other problem is very different, like for surveillance. And we'll pick like 2 different problems from these 2 different domains, and we will show how like different models of computing can be applied to solve such problems. And I will start with like a few slides on a very introductory computer vision and a very introductory deep learning, which is probably a buzzword. Like as you know, like nowadays So whenever you apply like machine learning, like we have, this deep learning nowadays, like, replacing the traditional machine learning. But at the same time, I will, emphasize that not really all the problems in computer vision or like in the allied domain of pattern recognition can be solved by just like deep learning, and often we require like classical solutions, as we will show in this talk. Okay. So introductory computer vision, like, so this is, well, I mean, kind of a definition of what falls within the scope of computer vision. So it's from this BMVA, which is British Machine Vision Association. In fact, they hold a conference called BMVC, British Machine Vision Conference. So it's concerned with the automatic extraction, analysis, and understanding of useful information from a single image or a sequence of images, could be a video, and it involves the development of a theoretical and algorithmic basis to achieve automatic visual understanding. So as I have mentioned at the beginning of the talk, so we have like concepts from mathematics, like physics, like statistics, and then of course like double electrical engineering, computer science, like all pouring in to make this domain very rich, the domain of computer vision. And there could be, well, definitely this is an incomplete list. So I have just marked in green like the two domains on which I will be from these two domains, like I'll be picking up problems, one from each domain. So healthcare, surveillance, and biometrics, geoscience, remote sensing, robotics, and it's a long list again. I mean, there are you could just add on. It's several different domains. This is an interesting example, like I thought of like, showing you as, what we do in computer vision. For example, if you think like, just the very left, picture. So there, like we can, it deals with the classification problem. So you have to find like, okay, like whether like the picture contains a cat. Now, once you move from left to right, you see, the complexity of the problem increases. So here, like you see a red box. So this becomes like classification as well as localization. So where in the frame, even if you have marked the frame earlier that it contains a cat, so in the next frame you show like where in the frame there is cat. Now, the problem gets tougher when you move to the third frame here, third from the left, which deals with like object detection. As you can see, there are different objects like a cat and a dog and a duck. So you are really detecting different types of objects. The problems become even tougher, like because now you are not only marking the bounding box, but you are showing really the contour. So it's known as instance segmentation. So I just like to give you an idea about complexity of these problems. I mean, when as human beings, like we can easily do this, right? But it's not that easy for a machine to do this. So there lies the challenge. Here is another problem where we are trying to detect like the faces, in a picture, and then you can see like, for example, there could be some misses, like there's a miss here, but like mostly it's able to detect. And this is a courtesy from computer vision course material by Professor Richard Jaliski at UWash, University of Washington. So as you can see, like this, like really, a varied problem, like from the one which I have just shown. Now let's see what type of models, mathematical models, computing models we apply to solve computer vision problems. Well, it's like it's really big variations, right? Like we have like graphs. Often we model problems in computer vision as rough cuts, rough matching. We try to find similarity by doing a spectral analysis of graphs. A game theory using Nash equilibrium. Level sets, again, I have highlighted in green because in one of the problems I'll be discussing, I will show how we apply level sets. So these are called active contours. Like the term active comes from the fact that the contour is changing. So that's why it's called an active contour. Then we have this differential geometry like mean and Gaussian curvatures, computational geometry, the Delaunay triangulations, Voronoi diagrams, and so on. Frequency domain signal analysis, signal processing, 2D, 3D, discrete cosine transforms, a lot of linear algebra, optimization, spectral clustering, eigenanalysis. Of course, from statistics and probability, like where we use, let's say, particle filtering, random walks, Nystrom approximations, Bayesian formulations, and again, I will use like in one of the problems like properties of distributions, classical machine learning, where again I will use metric learning, and we have random forests, support vector machines. Again, these are just like some samples like what we use to solve problems in computer vision. And then deep learning, like buzzwords like nowadays, but we have to be cautious like in terms of using our resource. First of all, when you apply deep learning, like you need good computational resource, because you need a lot of training. You need to provide your system a lot of training. And then nowadays, like very recently, let's say in 2020, 2021, we have more problems like explainable AI, interpretable AI. So I mean, just applying deep learning and getting good results may not be good enough. So in competitive places, whether it's a conference, it's a journal, they want to see really how you are applying deep learning, why you are applying deep learning, and so on. Here we will use like one model of deep learning called segment. So whatever I have marked in green in the previous slide and in this slide, these are like things I will be using as like solutions for the problems we are going to solve over next 25 minutes or so. And then I thought of including some slides on introductory deep learning. So what is the problem with the traditional features? Well, if you think of a computer vision problem, generally there are two broad aspects. So one is the descriptor, like how you describe your object, which is in computer vision jargon known as features. And the other is like the labeling problem. So let's say you have an the object detection. So it's whether it's an cat or a dog or a duck. Or let's say you are marking a face. So you are going to each frame in a video, and then you are marking like each pixel, maybe like whether it's a face or not. So the second part is mostly a leveling problem. Of course, there could be things other than this. For example, like if you do a tracking, then it's not exactly leveling. Well, you can think of it as a leveling problem, but it's not exactly leveling. But the main component, I mean, even if it's not a leveling problem, if it's a tracking problem, still you will have these descriptors. That's very important. So the problem with the traditional, or so to say, handcrafted descriptors or features are they are very tedious to develop, and then they are pretty application dependent. So there is not much flexibility that what you have developed for one application is easily extendable to another application. So deep learning seeks to learn features automatically through multiple layers, and it's extendable. So let's say for like very different objects, maybe like a medical image. Though in medical image there are other problems, like if you have scarcity of data, then the deep learning might fail. But let's assume like we could do. Then it's not that for a medical image you have to extract some handcrafted feature, which is very different from an traditional, let's say, object detection, where maybe the features are very different. So the deep learning, if you give this input to a deep learning paradigm, then you can have these deep features extracted for you, which is really good. So these are extendable, and also these features are very rich. So we will show, for example, here, as you can see, this is face, and then you have different layers, and then we have, so there is one input layer, there is one output layer, and then there are a lot of hidden layers, like which are multiple hidden layers. And if you use more number of hidden layers, then you solve like more nonlinear problems. A very simple example would be if you, let's say, try to separate like a pattern which is following an AND or an OR distribution, then you can simply draw a line to separate them. On that, for these type of classifications, like you can use a network which have maybe just an input and an output, really don't require any hidden layer. But if you have patterns distributed according to XOR or XOR, then these are no longer linearly separate. So you need to have maybe a combination of lines to separate the points based on their levels. So in such scenarios, if you want to apply machines to group, then you have to incorporate like more than one layer. Between input and output, there should be another layer at least. So that gives you an idea that the problem becomes nonlinear. You need to have intermediate layers, and then when the complexity of classification increases, then you need to have more layers. So each layer is represented by as a series of neurons and progressively extracts like low to higher level features. So here, for example, you can see that these are like low level features, and from there you can have mid level features, you have high level features, and you can have like trainable classifiers. So you have more distinct patterns, and actually this image can come up as a combination of these distinct patterns. So the deep learning gives like much better description as compared to like the traditional features. There are many different deep learning architectures. Like one very important class of architecture is given by or denoted by the convolutional neural network, CNN, which is a deep network, and that can take an input image, assign importance. So we have these learnable weights and biases to various aspects or objects in an image, and you can differentiate from one object to the other. Can learn multiple layers of transformations and basically or progressively can extract like to each feature. So here, let's say you have the neurons in the convolutional neural net arranges the neurons in 3 dimensions. You have this input, and then you have this depth, height, and width. So every layer transforms this 3D input volume to another 3D volume. And as you can see that the red input layer holds the image. So the width and height of would be the dimensions of the image, and depth is basically, since we are doing RGB 3 channels, so that would be really the depth. Here, like this is a structure of a neural net, like you have a feature, learning, you have this convolution, this is rectified linear unit, like we'll have some more slides later on. Then you have like pooling, like try to get a response from a region, and you keep repeating this, like so you can see a repetition of convolution, rectified linear unit, and pooling. And then here, like it's a classification, you make a decision, for example, as which is a car or truck or van or bicycle and so on. So this is basically the labeling part, and this is really the description part. So what happens is you have so this is, I think, probably a familiar picture. Like you have a set of inputs which are weighted by, so set of inputs like xi's and set of weights like wi's, and then this is a cell body, which, so this is of course an electrical analog of our neuron. So we have this summation I wi xi plus the b, so there's a bias, and these are the weights, and then you put f, which is an activation function to model like the synaptic nonlinearity, and then you get the output. So here is an example of activation function, and for deep learning, the most important activation function is called ReLU, rectified linear unit. As you can see, this gives you like non-negative output because it's like max of 0 and z, which eases. And what is the utility? Because if, let's say, you allow this to grow, then the value is increasing beyond your control. So you restrict it to a certain range. Now, how deep learning, because whatever I have presented so far, probably two very different things. Like one is I started with introductory computer vision, and then I went to introductory deep learning. So where is the relation? Well, so how deep learning can boost computer vision? There are more than one ways. Like you can have, let's say, better feature extraction and representation, and then you apply your some classical solution for labeling. You can also have a coarse to fine segmentation, which we will see. So let's say some initial good results you get from your deep learning, and then put that as an input to maybe a classical paradigm, and then you get a finer results. Then also you can do, let's say, ensemble learning, like multiple CNNs you can combine, or like, let's say, transfer learning, for example. Okay, so I missed that. So you can integrate like convolutional neural networks or deep learning with other machine learning algorithms. Like in one of the problems we worked, like where we kind of mixed deep learning with random forests, and we showed that that gives better results. Transfer learning is very important. So you have, let's say, knowledge from one domain, and then you transfer to the other domain. Because, well, I mean, if it's really very different domain, then you cannot transfer. But sometimes what happens, like you have scarcity of data. So from one domain, like you get the knowledge, or you get the level data, the training, and then you transfer to like the other domain. So So the transfer learning becomes very important. So the first problem, which is from healthcare, and which was joint work with the National Cancer Institute in Kolkata, is about lung nodule segmentation from CT images, which is like computed tomography images. So this is a statistics like which shows that lung cancer is one of the largest causes of cancer-related deaths worldwide. So it causes 1.76 million deaths in 2018. Like I haven't updated the statistics, but this is about the time we were doing this research. So we have this statistics from WHO, World Health Organization. So the lung nodules are precursors of lung cancer. And if we can detect early, then that increases the chance of survival. So for any computer-aided detection step or a CAD system, we need to segment. So you have to find out your object of interest. So you have an image. From there, you have to mark that this is the lung nodule. And then once you have that, which I will not cover in this talk, then you can mark it as, classify it as a benign or a malignant. So the CAD system helps radiologists to detect like lung cancer, especially like they increase the throughput. And generally for medical imaging, you always try to have a human in the loop, because you get the results, you validate the results by the expert. It's not about replacing the expert, but about assisting the expert. So there are several challenges, because we have to deal with low contrast, presence of noise. We have other pathologies which are similar to nodules, variability in shapes of the nodules, because there are different types of nodules, and the location, like where really a nodule is attached, so that becomes difficult. Nodules attached to pleural surface and vascular structures. So these are some shortcomings of existing works, like for example, they requires huge interaction from users, like fails to segment some specific nodules, manual initializations. Like if you use the level set based methods, we talk about that, then you have to manually initialize. Then we also have some deep graph cut, as you can see from the name. So the mix, like the deep learning and graph cuts. In fact, like we were inspired to some extent by that work. So we thought of, since lung nodules are very small structures, so if we use like active contours, that would be good. And from the family of active contours, level set is the best one because it can handle like changing topology. And we can mix like deep learning with graph cuts to have, mix deep learning with level sets to have good results. So the proposed work is we want to have a coarse to fine segmentation approach using a synergistic combination of deep learning and shape-driven level sets. So here are the contributions, like we have automatic initializations. Generally level sets we have to manually initialize, but what we have done, like we took the output of deep learning network, the core segmentation, and from there like we initialize the level set. And then how the level set would propagate. So that is given, or that is controlled by some shape factor. So we have a shape-driven level set which mines shape information of the long nodules. And then here like we started with the juxtapleural and isolated nodule. So we showed that a combination of the same framework can handle like the juxtapleural and isolated nodule segmentation. In fact, like again, this I will not show in this talk, but just to tell that we have actually, also worked on an extension of the problem, and more interestingly, in that extension, we used like fully level sets. So there, like we have shown that level set based formalism can detect like very different types of nodules. But anyway, this was our first, and since here we combined, I will have particularly chosen this to show that how we can really combine like a deep learning framework with a classical framework. So here you can see the schematic of the proposed work. Like we have the city image volumes, and then we have this long segmented image. So this is done for us, but then within the lungs, like where is the nodule, which itself is very challenging. And then we have a segment, it's an encoder decoder network, and we have an output image. As you can see, there are 4 segmentations, and then we apply like level sets to fine tune the segmentation, and we get the final results. So this is like the shape information. As you can see, this is like it's pretty well fitting into the contour of the nodule. So here are some pre-processing done. Like for example, we have to, for a deep network, you need to resize like the images to fit into the network. And this is your segment, which is a convolutional encoder decoder. So here, like there are a set of steps. Like each deep network has a set of steps. But it extracts, in this case, what will happen, it will extract like good features, and then it will level also. So we have already the segmented nodules as the output. So it consists of, okay, so why segment? Because there are many deep learning networks, but there are some reasons like why we went for like segment, or why we chose segment. Like it consists of sequence of processing layers, encoders and decoders, and one key ingredient is the use of max pooling. So that's a particular feature. Like, so from a region, how to get the response, you can have average pooling, you can have max pooling. Then it has a low memory requirement also compared to other networks, and so on. For example, the number of parameters from other networks, it's reduced from 134 million to 14.7 million. And the encoder network reduces the feature map size, leading to lossy image representation that reduces the computation as well. But then the price is with blurred boundaries, but then the decoder network upsample. So then we have like a better resolution to achieve the same resolution as the input image, to have the same resolution for the output image as that of the input image. So another benefit of max pooling is the translation invariance over small spatial shifts, because that's important. Like if you have some transformations on an object, then you should have like there should not be a problem in terms of recognition. Then locations of maximum feature value in each pooling window, and okay, so there are some details. And then there is a softmax classifier which finally classifies each pixel. So that means it answers the question whether this pixel is a nodule or not. And here are some results like the port segmentation, as you can see, the segment output. And then from there, we simply sort of mark really automatically, like, some positions within it, so that we initially take these as the starting points for the level sets. So this is, the level set evolution, as I have said, that this can handle like changing topology. As you can see, the active contours means like the contour can grow or shrink, so that's the contour is active. And as you can see here, like it breaks in 2D or like in 3D, like there are like separations and so on. So this is handled by the level set. So this is like some details. So you have level set function z as phi of xy t0, where the xy plane contains the contour and z is called the signed Euclidean distance. So it essentially tells you that whether you are inside a closed contour, or you are outside the closed contour, or you are on the contour. So which is given by z equal to 0, which is the contour cross section. And here's a picture that how level set evolves. So as you can see, this is a level set surface, and this is marked as you can see, the 0 level set in blue, and then it sort of like grows. As you can see, these are getting merged here. So over like time, as you can see, the time change is equal to 1. But then still, like the blue is like the 0 level set. So the contour is always marked by the 0 level set. So what happens is, like, if you can use the contour to mark your segmentation boundary. So how do you mark? So there should be some guidance. We will see there would be an energy function, what would be the driving force, and so on. So we have used like level set for fine segmentation, as if you use segment, it gives some false positives. Certain things like which are actually, I mean, we have this another motivation, like, so if you use like segment or things like that, then it gives you like your little bit over segmentation, and whereas level set gives like a little bit under segmentation. So that kind of complements the other. So here is the the energy function. As you can see, there's a distance regularization term. There is a energy along the length of the 0 level contour, and this is like energy of the area term that speeds up the motion of the 0 level contour. And there are like different expressions for these terms. For example, there's an age indicator function, so that level set is attracted towards the age. Then there is like the length term, where you have this Dirac delta function, the area term, even a Heaviside function for the evolving contours. And then we bring in like this we bring in the shape factors. So we have the perimeter and the circularity, and then we combine them in form of a weight, and then we use them to as you can see, we have incorporated that in the area term as a weight to the Heaviside function. So I mean, essentially the goal is to drive the evolving contours, or reward like the energy function of the evolving contours like towards the nodules. I'll show some pictures. So this becomes like the total energy function, and then this energy function can be minimized if you solve like a gradient flow equation, which is the partial derivative over time. So as you can see, let's say this is a synthetic image and this is a real image. So what we try to do is we try to have the level set should grow for the object of interest faster, and the level set should be sort of like make like stagnant in other objects of interest. So what we do is, like, since long nodules are more or less like the circular objects, so we try to have the level set grow towards their boundaries if the object is circular, rather than, as you can see here, as compared to, let's say, something like as a star shaped or like oval shaped and so on. So in both synthetic images, and then they tend to be large compared to other noisy blobs or other pathologies. So large circular object gets priority. So that's the main thing. And how we have achieved that is by incorporating this perimeter and circularity, which I have shown in the previous slide, to guide the evolution of the level set. And regarding performance measures, like there is some publicly available data set. As you can see, these are like the ground truth. So it's a annotated result, and then how we matched, what extent. As you can see, if we use like the segnet, this is the dice similarity score, which is 0.67. If we use like just the shape-driven level set, like we have dice similarity as 0.64, as you can see, this is kind of a over segmentation, this kind of under segmentation, and this really matches with the contour. Then we have this as pretty high 0.88, which is a combination. And here are some comparisons, like it's the error rate, like it's another metric where you can see like our error rate is minimum. Also, like comparison for isolated nodule and juxtapleural nodule. Also compared to learning-based algorithms, like we are doing well. And there are some visual results, as you can see, that these are the ground truth. And then in the very last column, we have the proposed method. These are some level set techniques. This is the segment, and you can see that this matches well. So the last column matches pretty well with the first column. So we have an end-to-end vision system for automated segmentation of pulmonary nodules, and we combine like convolutional neural network with the level set. So this was published in Patent Recognition Letters. So the second problem is on open set person re-identification, which is a very different problem. By the way, like I mean, how much time I have? Like, is 10 minutes fine?
Yeah, here you have 10 minutes.
Okay, thank you.
12 minutes, rather 12 minutes.
Thank you. So this is a very different problem, which is on person re-identification. So let me just show, like, okay, so what is person re-identification? So suppose like there is a campus, for example, if I think of my university, and let's say people are entering through one gate, and then we don't keep track of them in between. So there is sufficient temporal discontinuity, and then the person leaves through the other gate. And maybe when he enters from one gate, maybe the picture is taken by one camera, and when he or she leaves from the other gate, it's taken by another camera. And these are called like and what I mean, the goal is when we are looking for that person, like we are trying to find out like whether that person is there in a set of images. So there is a set of images called gallery images, and there is an image which is the query image or the probe image. But the problem is we have sufficient temporal discontinuity between the visuals of the same person. So as you can see, maybe you can change the dress, you can change the posture, the illumination might change. So we are re-identifying. We are again identifying the person, and there could be like several problems. Now these are like the general re-ID challenges, like where we have even as I have said, just pose, illumination, viewpoint, like there could be these variations, there could be occlusion problems, and so on. The resolutions of the cameras could be different, and so on. Now the problem becomes very difficult, tad more difficult if we think about like an open set, so which we actually try to address. So what is that? Like in the closed set, you can see similar things, right? Like all like trees. But how about like here? Like there are many different things we can see. And where lies the problem? Well, so suppose like we have trained a system with this husky and bull, okay? And then as a test, like we give these images. Now, if you look at these images, some of these images can be categorized into one of these bull and husky, but then there are some unknown images as well. So what we want is that we will be able to tell like these belong to the class husky, these belong to the class bull, but at the same time we should not forcibly put this two images into one of these classes that okay, they are somewhat more similar to one of the husky and bull classes, so let us put that, which is really not. So we put them as unknown classes. So the test image which let's say these are the probe images could be in the gallery set or not. This is like an additional problem, right? So we have to really think that to what extent we should allow the similarity, right? So here is it. So you have, let's say a sample which is more prone to husky. You see the 0.97, so you tell it as husky. There's another sample which is like giving a probability of 0.99 to belong to class bull, and you assign that. Similarly for the third one. How about the fourth one? You see this is still having one higher value, right? Of belong to the class bull is 0.63, but then like it should not be marked as belong to bull just because it has a higher value as compared to the husky, because in reality it's none of this. So you reject like if the value is less than a threshold, and if it's higher than a threshold, then out of these several classes, like the one which has the highest probability, like you assign to that. So this is the goal, to simultaneously detect and re-identify the interest or target persons. So if you, for an open set problem, as I have said, like the probe image may not be in a set of gallery images, so you can have several false alarms. So what we have done is we tried to have so this is from closed set to open set, like where we can have this unconstrained vision that the probe image may not be there in the gallery image. But when we tried to solve, like we tried to make like this open set to a closed set. So we introduced open set metric learning, and so there is like a large margin nearest neighbor algorithm which is very popular. So we make it for open set, and we reject like the probe samples using some properties of distribution, like reject some gallery samples to be whether they are not sufficiently similar to any of the probe image. So we remove them. So so here is like, here are the two things. So we detect like the pedestrian again using a deep learning algorithm, and then open to closed set conversion following Weibull rejection. So let's say if the similarity is really below a certain threshold, which is given by the properties of Weibull distribution, then we don't take that sample as a contender to match with the probe sets. In that way, we try to convert the open set to a closed set problem, and then we actually solve the closed set problem. So here are some mask detectors, and then so how you detect like the features. So these are some descriptors for the the persons like which you want to detect. Now here comes the trick. Like you have so this is the standard 11. So you have the Molar metric like between two samples, like so you have this xi(xj) transpose m xi(xj). So this is a covariance matrix, and in case of like Euclidean distance, it degenerates to an identity matrix. And then for the element and loss, like you have the combination of these two factors. So the the philosophy is this. So you have a sample, and then you have a set of target neighbors, and you have a set of imposters. So what you do is you try to pull the target neighbors towards it, and you push the imposters beyond the margin. So that's like the push pull. So the first one, like if the target neighbors are far off, then you penalize them, try to bring them close. On the other hand, if the imposters, they are nearby, there are small gaps, you push them, right? So this is like, as you can see, after the push pull, you see like the yellow, like the blocks, like yellow the circles, they're coming closer, and the red and blue blocks are, the imposters are moving apart. Okay, so that this large Weibull distribution for the rejection, this is from this extra value theorem.
Professor Chaudhary, you have 5 minutes more.
Yes, sure. So this is this is like the Weibull distribution. You can see the probability distribution of there is a long tail which we will make use of, and then we have the cumulative distribution function for the Weibull distribution. So what we do is we introduce a new loss function where we have one component coming from the Molar metric, and the other part like is coming from the Weibull distribution. So so if let's say this WKI is small, then the smaller distance between dissimilar pairs, that increases like the push factors. And then we try to have a regularization term to have like smooth boundaries, and then we try to optimize this loss function using LPFGS, which is like a memory efficient solver. So the Weibull rejection mechanism like this works in this way. Like you have a dynamic gallery set G, and then you have a likelihood based value like assigned to every probe sample. You try to have a pairwise computation and assigns a low probability value to dissimilar pairs in the numeric space. And so this is important. So this makes the open set problem to a closed set problem. So reject pairs with likelihood value less than a threshold. And then it becomes really a closed set problem, and then you try to find out like the best similarities. So here are some comparisons. So we have like a publicly available data set, and then like we try to find out like the detection and identification rate and the false acceptance rate. There are some standard measures, and we have to show the robustness by finding the area under the curve. Here are some detailed results. These are also given in the paper. More comparisons, and here are like some, as you can see, this robustness, like we put the values like the area under the curves. So we have a new metric learning here, metric learning model, which is like the LMNN, but that has been extended in the open set context. The concept of Weibull rejection has been introduced to convert an open set VID to a closed set, because the samples for which the likelihood lies in the tail of the Weibull distribution, so we don't consider them. So by rejecting them, we ensure that the probe image is indeed in the gallery images, and then we can further improve it. Can be further improved by introducing like nonlinearity through kernels, so on. So this is my conclusion. So I try to take you through a mathematical journey in computer vision. So we have solved two different problems, one in healthcare and the other in surveillance. And as solutions, like we have applied level sets, deep learning, metric learning, like the LMNN, where we use like the Molar metric and the push-pull, with Weibull distributions, and try to optimize that. I want to acknowledge my former PhD students. Like, so Rukmini worked on this lung nodule problem, so she is currently doing a postdoc at MD Anderson, and Arindam has got offered University of Bristol, UK, so he worked on the surveillance problem. I thank Dr. Shuparna Majumdar from Chittaranjan National Cancer Institute for helping us in this problem, and also thanks to MHRD and my university for providing the fellowships and infrastructural supports. So thank you very much, and if you have some questions, I'll be happy to answer.
Thanks a lot, Professor Chaudhary. So now the session is open for some question, comments, or some remarks.
Yes, I think Dr. Radhavendra Singh has raised his hand. Perhaps he will be asking some question.
Oh, sure, yeah.
Dr. Singh, you may ask.
Is there any question from the audience?
Yes, I have a little query, if may I ask?
Yes, please.
Yes, thank you very much. That was a very nice talk, Professor Ananda. So my query is regarding your first application. It was a very interesting application. I think maybe I missed something there. It was more of a segmentation problem. Where was the computer vision coming into the picture in the first part? Probably I missed your explanation.
Okay, so I mean the segmentation actually lies at the junction of image processing and computer vision. So for example, like when you try to let's say guide the level set, right, through the shape information. So these are like more towards the computer vision rather than like the traditional image processing. But yeah, I mean there are definitely overlaps with like the traditional image processing. But I would say the traditional image processing would be probably deal with problems like like the enhancement, blurring, and so on. So in that way, like the segmentation problem like often like falls under the purview of computer vision.
Oh, okay. Thank you. I actually thought that, unlike like your second application where you're going to identify and say this is a dog, this is a husky, and I thought maybe you're going to classify your nodule, saying that it is.
Yeah.
It's only a segmentation at the moment, which is an important step in vision. That's what you're saying. Right. Thank you.
And then after segmentation, of course, we are in other papers like we have classified like to let's say benign and malignant and so on.
And your machine deep learning is coming from coarsening, from coarse resolution to fine resolution. That's what you're going to use in your first application in deep learning.
Yeah, right. Yes.
Okay. Thank you.
So any other question?
You like the initialization for the level set. Like if you have like the coarse segmentation from there, you can initialize
Thank you very much.
So the manual initialization part is taken care of. Because one of the challenges in computer vision is automation.
Any other question from the audience? If not, Professor Chaudhary, can I have a remark a little bit? Your opinion, please. Actually, so in your last example, that is on the image re-identification. So you are using, you are talking about the Weibull distribution. Yeah, the people, I'm not very acquainted with this image processing, but the people who are working on growth curves, basically, so they are using various types of distribution, as for example, Weibull distribution. And now actually, I came across a paper recently whether they have provided a general class of distribution, and which includes not only the Weibull distribution, it includes several others distribution which represent the various types, because the various types of growth curves. So basically, in this image identification, in my opinion, so maybe not only the Weibull distribution, some other distribution may work on that. What's your opinion about that?
Very, very good question. I mean, so I mean here the main motivation behind using the Weibull distribution was that we want to put a threshold. So we basically, like, it was like an open set problem, like, which was making things more difficult for us. So we tried to convert like open set to closed set. So by looking at the tail of the Weibull distribution, we tried to find out that if really that there are the likelihood between like two samples like to become similar, that's really less, we tried to discard. So we tried to use that particular property of Weibull distribution, and that was kind of linked to this EVT, or extreme value theorem. So I think like the intuition probably is to look at distributions which have heavy tails, basically. So that like we can try to model, because so we are trying to restrict the similarity. Like if the similarity is really below a threshold, then we say, so it will still have some value, right? But we don't want to classify it. So we are trying to reject that sample, and then we go for the actual similarity matching.
Okay. So if there is no question, I would like to thank you very much for your nice question. Yes, any question?
I think.
Dr. Raghavan Singh?
Yes. Yeah.
Hello.
Yes.
Yes, please.
डॉक्टर राघवन सिंह, आनंद सर, मैं ये पूछना चाहता हूँ कि इमेज प्रोसेसिंग टू डेवलप टू मैथमेटिकल मॉडलिंग। आनंद जी, मेरी आवाज आपको पास सुनाई दे रही है?
Yes. Yeah. So please, could you repeat the question? Like, so the question is
image processing the model in neural network.
Image processing models in neural network.
पर्टिकुलर न्यूरल नेटवर्क पे कोई मॉडल है जिसपे इमेज प्रोसेसिंग का काम कर सके?
Oh yeah, several actually. So as I've said, like so the neural networks are very much used in image processing or computer vision. So there are many actually. So all the computer vision problems, let's say classification, segmentation, and these are like two broad computer vision class of problems where a lot of like neural network and nowadays like deep learning has been used.
Okay. ठीक है सर, thank you.
I think there was another question in the chat box. Oh no, that's not a question. I think there was some question regarding like morphology or something, or maybe I'm not sure like whether that was posted or not.
Yeah, I think that was posted. Now I cannot find it out.
Yes. Now I find. Yes, mathematical morphology used in computer vision. Yes, of course. Yes. So I had one collaboration with Dr. Michael Wilkinson at University of Groningen in the Netherlands. So he precisely used in mathematical morphology. So the answer to your question is of course yes, because there is in fact a dedicated symposium called International Symposium on Mathematical Morphology. So which deals with these typical computer vision problems. So where they, in fact, my collaboration was we are trying to mix like morphology with graphs. So I mean, so let's say the applications like where you are trying to detect some fine shapes. In fact, like this is like the Lang nodule could be one problem, like where mathematical morphology could be very handy. So the answer to your question is of course yes.
Any other question from the audience? If there is no question, let's have a big hands
Thank you.
to Professor Chaudhary. Thank you very much, Professor Chaudhary,
Thank you, Professor.
for your time and helping us.
Thank you, and thank
It's
you.
very nice. It's a very nice stuff. Very nice stuff.
Thank you very much. Thank you.
Thank you.
So maybe with your kind permission, like if I can leave.
Yes, yes, you can.
Thank you. Thank you.
Thank you.
Thank you. And I wish the conference all the best. Thank you.
Thank you very
Okay,
much.
thank you very much.
Thank you.
So let me thank both Professor Chattopadhyay and Professor Chaudhary for this wonderful session. And we quickly move on to the next invited talk. This is going to be our invited talk number 6. And this is a prestigious Inertian Memorial Lecture. And it will be delivered by Professor B.V. Ratish Kumar from IIT Kanpur. And the title of the talk will be Stabilized Variational Multiscale Finite Element Analysis of Coupled Brinkman-Stokes Transport Model. This session will be chaired by Professor Kajol De, one of the vice presidents of Calcutta Mathematical Society. So I request Professor De to start the session. Professor De, you are muted, I think.
The sound is not coming.
Professor De, your sound is not properly coming. We cannot hear you. No, it's still not coming. Professor De, can you hear? Some technical problem, I think. Let me wait. Let us wait for some moments. So in between, as she joins, you can see that this has been particular slide has been shared. That this is all the details of this particular Inertian Memorial Lecture. And this is a short sketch of the biography of Professor Shin. And as I continue with this, it's a quick view of this thing. I'm not going to read it out. You can find it. Everything is there detailed in this slide. So let us wait for a certain while in between if Professor D joins. I think she has joined. Yes.
Can you hear me?
Yes. I can hear. We can all hear.
Okay.
Please.
Thank you. Good evening, the dignitaries and participants here. I invite you to the invited talk number 6, which is the Inertian Memorial Lecture, which will be delivered by Professor B.V. Ratish Kumar. Let me introduce him. He is a professor from the Department of Mathematics and Statistics from Indian Institute of Technology, Kanpur. He has done his PhD from Sri Satyasai Institute of Higher Learning, Prasanthi Nilayam, Andhra Pradesh. And his research interest is applied mathematics broadly, namely finite element analysis, partial differential equations, numerical analysis, parallel computing, computational fluid dynamics, computational biomechanics, and image processing. The title of the talk, today's talk, is Stabilized Variational Multiscale Finite Element Analysis of Coupled Brinkman-Stokes Transport Model. So I invite Professor B.V. Ratish Kumar for delivering the lecture. Over to Professor Ratish Kumar.
Thank you very much, Professor Kajal. I hope I'm audible.
Yeah.
Yes. So let me first, I will attempt to share my slides here, and then I think we will move on to the whole thing. Okay. Can you see the slides? Can you see the slides?
Yes.
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 Okay, that's great. So at the very outset, I'm extremely thankful to the society for inviting me to be the part of this event and giving me the honor of delivering this lecture, which is a very important lecture, Professor Nikhil Ranjan Sen's, in the memory of Professor Nikhil Ranjan Sen's. And I'll call this as a humble and reverential tribute to Professor Dr. Nikhil Ranjan Sen. So his fantastic academic and lifespan starting from May 23rd, 1894 to January 13, 1963. So I want to go over, he's such a great gentleman and great academician who has contributed in a very rich way for the applied mathematics of our country. So I would consider it as a great privilege to deliver this lecture. And prior to that, I would like to spend a couple of minutes in recalling some of the important contributions that he has made to the community of applied mathematics. Let me start off with his with the details on his basic birth details. He is born to, he was a son of Sri Kali Mohan Sen and Mrs. Bidumuki Devi. He belonged to Dhaka district, now in Bangladesh. And about his early education, so he's a first grade pass out from Rajshahi College in 1909, a BSc Honours in Mathematics from Presidency College in Kolkata, 1913, MSc in Applied Mathematics, Kolkata University, 1915. It's an early job. He was a lecturer in College of Science and Technology, Calcutta University, 1917. He's a member of Board of Higher Studies in Applied Mathematics, 1918 and 19. So let's now focus on his academic career. Let's start off with his doctoral research career. He is double doctorate. His first PhD was in 1922 for his work on potentials of uniform, etc., from Calcutta University. And he obtained his second doctoral degree in 1924 for his work on general theory of relativity and cosmology from the University of Berlin, Germany. Few of his achievements, he has several achievements. I'm going to mention few. It's very important for us to recall. He is popularly revered as the father of Indian applied mathematics. So I indeed consider it as a privilege to talk and to make this as a tribute and a talk in this preliminary lecture. So he's a founder of Calcutta. He's considered as a founder of Calcutta Society of Relativity Theory, founder of Calcutta Math Society, founder of INSA. I think everybody heard about INSA. It's a PhD from the University of Berlin, doctoral student of Nobel laureate, Professor Dr. Max van Loo, a physicist and a close friend of Dr. Albert Einstein. So Professor Sen was also quite closely linked to Albert Einstein. So a few research interests of his, I'm not going to read it out. There are plenty of research interests where he has made a lot of contributions. In fact, my talk, I have chosen two of the specific subjects of Professor Sen. Laboratory of Numerical Analysis. He was also one of the first persons in our country who said that numerical analysis is very important, and he was working very hard to build up a laboratory on numerical analysis. And he was one of the very first persons who had this vision that applied mathematics and industrial mathematics, they are very important topics to fine-tune, make good many contributions to industry. And fluid dynamics was one of his very important topics. and research contributions. He has made rich research contributions in that direction. That's why I highlighted this. In fact, my talk is also going to get related to these two topics, numerical analysis and fluid dynamics. And it will be not correct on my part without listing some of the contributions that he has made. The very first article, when there was very few applied mathematicians who could really guide and tell, Professor Sen took lead in the limited setup that was existing those days in Kolkata. And he wrote his first article in 1918 on the potentials of heterogeneous incomplete ellipsoids and elliptic disks. And his second article was on potentials of uniform and heterogeneous elliptic cylinders at an external point. So he had several important contributions. I'm not going to read it out, but I would like to highlight, this was a highly dedicated gentleman, highly dedicated academician who, despite the several odds, was able to pursue under the guidance of great leaders. I will show you the photographs of these leaders. It's very important. You all will, I think many of you will be familiar with all these great figures here. Professor S.N. Bose, who is very sitting here. These are all the stalwarts, as you will see. Professor J.C. Bose, Professor J.C. Bose, Sir J.C. Bose is right here. And from the left, we have Professor Nag, Professor J.C. Ghosh, Professor J.C. Bose, Professor Meghnad Saha, Professor S. Datta. And here is this great gentleman, N.R. Sen. And you have J.N. Mukherjee, S.N. Bose, and D.M. Bose. I am sure that all of you will be very proud for the contribution that these great gentlemen have made. And he belongs to this wonderful class of great academicians who have really contributed. So indeed, it's a very great honor to speak in this particular memorial session. And I would definitely like to acknowledge this research paper, which has recently been published in 2021, which talks richly about this great academician and mathematician who was behind INSA, N.R. Sen, the father of Indian applied mathematics. So I have picked up all these details from this contribution made by these great academicians, Saibal Ray, Utpal Mukhopadhyay, Ranjit Singh. So thank you very much for this, giving me for this opportunity. And now I would actually like to get into the actual proceedings of this particular event. So let me share the talk for this. So this particular session, I hope you can see this session, this slide now. I'm now moving into the main talk. Madam, can you see this? Can you see this slide?
Yes, it's visible.
So now I'm extremely, once again, thankful to the members of this society for inviting me, and especially to Professor Malay Banerjee, who has been instrumental in giving this invitation to me. Thanks to the society and thanks to Professor Malay Banerjee. So the title of this talk, as have wanted to make it a tribute to this great academician, I've chosen it a combination of numerical analysis and fluid mechanics. So it's a stabilized, variational, multi-scale, subgrid finite element analysis of coupled Brinkman-Stokes transport model. As you would see, the first part of the title is really dealing with the numerical analysis, and the second part of the title deals with an important fluid model. That's a coupled Brinkman transport model. Now, let me straight away, without wasting time, I will straight away get into the contents of the talk. So I will be trying to elaborate on, I'm going to use the numerical method, which is finite element. I'll give you a glimpse of it without wasting much time there. And if, as mathematicians, we are not going to blindly use any numerical tool without assessing and saying how good or how bad we are with it. So that's where we are going to do so-called a priori error estimation and a posteriori estimation, which essentially helps us to quantify the amount of the error that one would make while using a numerical tool in understanding or in unraveling the truth hidden behind the physical model describing the fluid phenomena. So these are all the mathematical notions which helps us to assess our analysis so that we will be able to get right kind of an interpretation from the solution. So this all goes a priori, a posteriori estimates in the regular energy norms. Then we move on to the L2 norms. Then whatever has been introduced, they have limitations. So we go on to the state-of-art methods, which is currently very hot topic. That's a stabilized methods. So the conventional methods have limitations. I will show you those limitations. Then we'll move on to the state-of-art method. Then I will introduce our own contribution, which we have made, subgrid multi-scale stabilized technique for transport equations, which we have successfully handled, with which we have successfully handled subgrid multi-scale method for couples, Darcy, and transport equation. Now, to drive home the concepts, I have chosen to begin with a very simple problem, which is a one-dimensional transport problem. As you all would see, it's a reaction diffusion equation. Here you have a reaction, here you have the reaction term, this is the diffusion term, this is the advection term, right? In this case, this toy model is chosen to drive home the concepts, and very soon we will try migrate to the realistic models. Now, as you see here, these coefficients here for our discussion purpose, we will take all these coefficients to the real coefficients, and where A is greater than 0 and B is greater than or equal to 0 and C is greater than or equal to 0 there. And our domain of interest for this toy problem is a line of length L1, which is in R. So the boundary condition, since it is a non-homogeneous 1D problem, here what you see is a homogeneous Dirichlet boundary condition. Problems of the reaction diffusion, advection reaction diffusion problems of this kind rarely arise in physiology, biomedical engineering, while one is dealing with mixing and transportation of drugs or toxins in blood vessels, or while one is dealing with hydrology or environmental science, like problems related to contamination of pollutants through rivers, in groundwater, so on and so forth, or in chemical engineering. So for example, let's look at a real life problem. Here we have a blood flow in an arterial system, and we have here our extracellular matrix, wherein probably there are some tumor cells which are present here, which are gradually growing and cutting down. There is a declination of the oxygen level. So we would like to actually send a drug which would diffuse through these walls and attach these tumor cells and tries to do some remedial features. So what we do is, in our modeling, what we are going to do is, we consider this as a flow, which is a blood flow, which is modeled by Stokes or Navier-Stokes or non-Newtonian fluid. And here, this extracellular matrix is treated as a porous domain. And we have an interface here. When a drug is introduced, the drug which is being carried along this stream diffuses into this extracellular matrix and tries to treat this. So essentially, we need a model to assess this whole drug diffusion into this extracellular matrix and as it is being carried out. So we are going to have a couple Darcy-Stokes problem where that Stokes is going to take care of the flow in these vessels, and Darcy model with advection of the solutes, that's the drug for us, is going to be modeled by the system which I'm going to talk. So this is one motivation example which is of real life importance. Another important example that we can take from the engineering context is this. Here we all know that pollution which is coming in the groundwater slowly. Here what you see is a typically hydrology situation. There are pollutants which are getting transferred down into the earth, and in this they get diffused and into these soil layers. They slowly propagate, they get diffused and slowly migrate. So this flow is modeled by Stokes, and the solutes or the pollutants which get diffused into this soil layer, that's modeled by the Darcy model. So that's how the model which I'm going to introduce to you has a lot of relevance to the reality. Now let's get into the mathematical setting for looking into the basic model which I have introduced. So firstly, we have said that in the model which I have shown you here, so we have already assumed that C is going to be greater than or equal to 0. So now certain assumptions on the model. Firstly, when with this model, what we have here is called as the strong form of the model, because it's a differential equation which is actually looked at. Usually when we want to solve these problems, it will become costly. If you want not the toy problem, when we go to the real problem, so we are talking about the setting which will help us when we actually go into the realistic problem. So here what we do is we convert a problem from the strong form to the so-called the weak form. For the weak form of the problem, we need to choose the appropriate spaces. In this case, as you see here, we have second order derivatives present in this. So we are trying to find a solution which is vanishing on the boundaries and is also second order derivatives exist. The strong form of the problem demands that we should search for a solution which is at least twice continuously differentiable. We probably can relax a bit, and it's also vanishing on the boundary. So our search for the solution is going to be in the space C2 omega. Omega is our domain, intersection C0 omega. So this is a slightly stringent space conditions. Is it not possible for reducing or relax this requirement on the space? Yes, it is possible. So we weaken the problem. So from the strong form of the problem, we go into the milder settings. These milder settings, now our settings is going to be, we are now going to consider the weak form of the problem, weak or variational form of the problem. What you see here is this is the weak or the variational form of the problem 1, which I have already shown. What is this? This is nothing but the bilinear form. This is the bounded linear form on the right hand side. What exactly is this B of W5? This expansion for this is provided right here. So this is usual inner products. What you see here, these are the coefficients and these are the usual inner products. And right hand side is again an inner product of the given data F with the weight function W. What we have done, we have converted the differential problem to a variational problem here. So by this, what has happened? What we have got is we have moved from the differential equation to the integral equations wherein some differentials are sitting, but then here we don't have second order derivatives, we have first order derivatives. So the requirement that C2 omega intersection C0 omega is now reduced. We are now going to look for a solution in the space H1 omega, which is nothing but set of all functions which are L2 and their derivatives are also L2. In addition to that, having defined this, our solution space is going to be V, which is H1 0 omega, which means that all those functions which are H1 omega and they vanish on the boundary. So if we were to look back into the given model, we had a homogeneous Dirichlet boundary condition, and that's when we search for the solution in this space, that's going to be taken care. Now let's look at, we have made some assumption that C is going to be greater than or equal to 0, and B, the way it is going to turn out to be, if we were to look at this B closely, you will be able to justify that this B is going to be positive definite. So for which, in this you can verify it turns out to be positive definite, in which case 1 and equivalently 4 will have a unique solution. This uniqueness in the solution guarantees that the given solution at any in the entire space is going to be bounded by the given data. So this, in other words, is called the well-posedness or a stable model, which says that if we were to look at the mathematically this model, which has been converted subsequently into this form, is a well-posed model because and it has a stable solution. So this is a very important condition which for this particular toy model, based on the modeling considerations, this is all gifted to us. But in reality, when you go to a model, this will be all the things which we need to really verify and ensure. Now, if you go back to your basic model, and if you take your B to be 0, that means you are knocking out the advection part. There's only diffusion and the reaction term. If you knock out the advection part, it turns out that the bilinear form that you have here, if you knock out this term, turns out to be symmetric. So if it is not the case, it will be non-symmetric. So in either cases, we have the Lax-Milgram theory, which under certain conditions satisfied by the bilinear form B and the linear form L will guarantee the existence of the solution and the uniqueness of the solution. So in this toy problem, it turns out, what are the conditions? Firstly, the bilinear form should be continuous, which means that the bilinear form is bounded in this sense. For the V norm, the norm in the space, and that's the phi norm. So then the bilinear form should be coercive, which means that bilinear form should satisfy this condition with respect to the V norm, that the solution space norm. And the L function should be a bounded linear functional. So this is the basic requirements for the Lax-Milgram theory. It so happens that in this particular type problem, all these things in this for this bilinear form, they all get satisfied. The B satisfies the continuity coercivity condition, and L satisfies the bounded linear requirement of Lax-Milgram. And the gift is that the solution for this problem exists and it is unique. As mathematicians, we very well know that unless the problem is well posed, unless we are very sure the solution exists for the model, we are not going to deploy it for any practical problem. So for us, luckily, this Lax-Milgram theory comes handy to guarantee the existence uniqueness of the given model. So now, having done that, let me introduce for this toy problem in a very clear, in a nutshell, the finite element approach. What we do here is we do not solve the problem as such in the space V, which is infinite dimensional space. We jump from the infinite dimensional space to the finite dimensional subspace of it. What is this H? H is nothing but, given a domain, in this case, it happens to be an interval. I discretize it and cut into intervals. So the size of each of the subinterval, typical size is denoted by H, which means I'm going to now find the solution at the vertices of all these subintervals. In other words, from infinite dimensions, I'm going to jump into finite dimensional subspace. I'm going to find the solution at few finitely many points. So then I have to go back to infinity, correct? I have to go back to my solution. How do I do that? For that, I introduce the interpolation functions. So there's going to be some error in it. Once I find the solution to the interpolation functions at all these vertices, then I will be able to go back and find the solution. So when I were to discretize the domain from omega into small intervals called omega case, each of the intervals will have its endpoints. So they are denoted by the boundary. In the 1D case, in the higher dimensions, it could be edges or it could be faces. So depending upon your 2D or 3D. So HK is typically a typical length of an subinterval in 1D case, or in the case of the 2 dimensions, it could be the let's say the triangular elements or rectangular elements or pentagons are going to cover your domain. Let's say typically triangles are covering. The HK is going to be the diameter of an incircle or the circumcircle. That's typical measures one can take. That gives an idea of what is the size of a typical element, which essentially says that as H becomes small, that means the resolution, number of the points considered in the domain increases. So that's basically a subspace which can, as with a resolution, the degrees of the freedom of the subspace increases. So now we use this information and convert the given continuous representation of the weak form into the discrete form of the problem in terms of this discrete information that we have here. So we write the problem from the continuous setting to the discrete setting. That's the representation of the problem in the discrete setting. What you have is the discrete finite dimensional subspace of the infinite dimensional subspace V. Now we're going to solve the problem in the finite dimensional subspace. So we all know that we have made a big leap from the infinite dimension to finite dimensions. So how good is our solution? Is it any worthwhile solution at all? Because your problem is originally posed in infinite dimension, you have made a big leap of jumping into finite dimensions. How good you are? So that's where we have to guarantee that we are good enough. Of course, we are not going to be 100% good. How good we are? 90% or 20% or 100%, where we are lying. So that's where, so what we do is we convert the problem firstly into the finite dimensional analog, which turns out in this case to a matrix form Ax equal to B. By using all the information that I've told, from the continuous domain, you use all the information, reduce the continuous problem in the integral form to the algebraic form. I skip the details of it. This algebraic form of the given problem by use the discrete representation of the entire domain and the variables, etc. So now from an infinite dimension, we are in a finite dimensional setting, and it turns out to be solving Ax equal to B. How good we are with this solution? Can we really invert this matrix? Is this matrix a non-singular matrix? What guarantees? Yes. Lax-Milgram theory in the weak form guaranteed the solution. Now you're ending up with a matrix problem. Is this a well-posed system? Is this a non-singular system? Once Lax-Milgram guarantees, then it has to be invertible. This has to be non-singular. So what guarantees? What guarantees here is coercivity. Once the coercivity is guaranteed, the entries of this matrix will guarantee that it's going to be non-singular. So that's the subtle link between the Lax-Milgram theory and the matrix numerical linear algebra. One can also come to this stage and use the theory from numerical algebra to guarantee the solution. That's an alternate approach for guaranteeing the solution. After having said all this, the question still remains how good you are from taking a big leap from the infinite dimension to finite dimensional. Yes, how good I am? That's the solution in the continuous setting. This is the solution which I found in the finite dimensional setting. So the error between the two measured in so-called energy norm, I have to define energy norm, I will define the energy norm. Let's say it's a measuring quantity. I have measured it in some quantity called as energy norm. So this solution, what it says, if I presume that I proved it, then it says that the error measured in this so-called energy measure turns out to be bounded by a constant Cn, and h, which is a typical measure of an interval that's being subinterval or the domain subdomain size, that's h, which I talked about, multiplied by the p+1 norm of phi. Phi is nothing but solution variable, but we know that from our solution spaces, we are searching solution in these spaces. Therefore, this is a bounded quantity. This is a bounded quantity. Now, if this h, if the resolution increases, that means h goes to 0. More the number of the points, smaller will be the triangles, or smaller will be the subintervals, smaller will be the h. As the resolution increases, h goes to 0, which means that slowly my finite dimensional solution should go to infinite dimensional solution. It should go. So how good I am? Whether my solution is good to represent it, yes, as the resolution increases, it goes to 5. But how good I am? Will it say, am I 50% good or 70% good for the given h? That I cannot, unless I quantify my Cn and quantify this quantity, I will not be able to really quantify whether I'm 70% good or 80% good or 20% good. So this quantification is not possible by so-called a priori estimation. To quantify this quantity, I need to move on to so-called a posteriori estimate. So a posteriori estimate, what it does is, it gives a measure. I will be able to get here whole, and once again, what you see is the error measured in the energy norm, but then here what I have is RH and Ci and H. This Ci is a quantity, it's again a constant, but then this particular constant, I have an information. I'll be able to get a lower bound and upper bound on this. This RH, what I have is nothing but a residual. What is this residual? I solve the problem, I get a solution, substitute the solution back into the governing equations, that's the residual. So I have an information on this, I have information on this, I have some bounds on this. Therefore, I will be able to say how good I am. So these are all the notions which are currently used in all the software packages which are solving PDEs for realistic problems. They have this assessment done. So these are two important things which, after having proved existence, uniqueness, well-posedness of the problem right in the beginning, this numerator assesses our given numerical method, how good it is, how much I can believe in it, reliability of the method can be established by this. And this is very important when you're dealing with practical problems like drug delivery, etc. You need to know how much I can rely on all the computations. So you will be able to give reliability bounds based on this. So now this is, I'm going to actually show these things. So what I do is, I have a proof for this, but right now I'm going to skip the proofs. If time permits, I would come back and prove it. Otherwise, I would require the request the friends to come back to me. I will be able to tell the proof offline anytime. So here, I have a proof. I'm skipping this proof, but I will give you a sketch of the proof without going to the details. So what we do is, to prove these things, firstly, we will call this quantity phi h is the computed solution, phi is the exact solution, which we do not know. That's why we are computing it. We say that let E be, let's tentatively say that E is going to denote the difference between the computed solution and the exact solution, right? Now, see, here I'm going to get these two bounds. That's the notion. How do I derive these bounds? So phi h, now this, I said that I'm going to introduce so-called interpolation functions, which I constructed. Therefore, I am going to introduce these interpolation functions as I add and subtract. Now I have the difference between these two, the exact solution, computed solution, and the interpolate, and interpolate solution, exact solution. Now, why do I do this? I want to get these measures. So for that, I'm using the tools that I have. Now, what is this quantity? Interpolant of a given function. What does it remind? Approximation theory. The approximation theory gifts us with a lot of approximations on these interpolation errors. And what is this part? This is called as the auxiliary error, which I need to now assess it. So we call this auxiliary error as EH and the interpolation error as eta. the interpolation error, I use the so-called approximation theory. If results are available, from there I use it. Otherwise, I add new results to approximation theory to get an estimate on this. So my whole efforts are going to be in building up these estimates on these two things, which I'm going to skip it, for which I have to make a mathematical construction. So I have to go back to the given weak form and write it out in an amenable form. I write it out in this particular case as symmetric and skew symmetrics, because there is a symmetric part of it and the skew symmetric part of it. Then this is the energy norm. The energy norm is going to be nothing but our bilinear expression itself. So energy norm is used for the symmetric one, and for the skew symmetric part, we use the sup norm defined as an operator norm. So these two norms are used in assessing these two quantities, and finally we'll be able to arrive at this estimate. So these are the tools which I'm going to use it. And we also use the Cauchy-Schwarz inequality here. The skew norm is bound by this, by the very definition, this is bound by this. As you see, if we were to knock out the sup, this will automatically give this. From the definition, we arrive at this, and from the Cauchy-Schwarz, for the symmetric part, we arrive at this one, right? So this is all in the energies. This is in a skew norm, and this is the energy norm. Energy norm is this one. This is the bilinear form which I've already introduced. The skew norm is this. So I will be able to measure this in this quantity, and able to measure this in the energy norm to the bilinear form. So this is the proof part, which I'm going to skip it. We will be able to compute the quantities. These two quantities we need to compute. Either bound on this and bound on these quantities. So we will be, therefore we consider this, split it out. If time permits, I come back later. So we will be able to go through this proof and able to come up with the energy estimate on which we proposed here. So the energy norm, so this is some proof points which, if time permits, I'll come later. So the idea is to come up with this energy estimate on the error. So that
you have 10 minutes more.
Thank you. I will skip the proof. I will not take up the proof. I will just proceed further. So that's the final form of the proof in the energy norm. So similarly, we can also estimate the so-called a posteriori estimate, which is proof again. I skip it. Now these two things, once I'm able to estimate these things, what it does is it empowers me to go ahead with my methodology, which says that yes, your methods are going to be now going to work fine. You're able to say how good or how bad you are, and you go further with it. Now it seems to be all seem to be very nice. Now this is the measures in energy norm. There are also similar measures in the L2 norms, which I do not have time to go. L2 norm measures again are going to be similar to, so this is the L2 norm. So here I don't have an E there. This is an L2 norm. As you see, that's the L2 norm estimate, a posteriori estimate. Now I have shown all these things with the toy problem. Now let's move slightly one step further. What you have now is a two-dimensional context. This is a typical problem in hydrology. We have some transport of pollutants. For this problem, what you see here, the diffusion coefficients could be that there could be variable functions. I have a diffusion coefficients and advection term here, and a reaction term here. Now for this problem, again, we can go into the weak form setting. We have a typical advantage of that. Luckily for us, again, for this problem, Lax-Milgram comes to our rescue. Yes, provided you can show that this is going to be a bilinear form satisfying the criteria of Lax-Milgram, and this is the bounded linear form as per the Lax-Milgram theory, then it guarantees one can once again proceed with confidence that I am dealing with a well-posed problem for which solution exists. And now again, for the finite element theory, we'll be able to go with the methodology that I discussed in brief. You'll be able to once again get up with this energy estimate, which is a priori, and L2 estimate. Here you see the energy norm and the L2 norm for the a priori, because here I don't know C, but this is bounded quantity. I don't know C prime, but this is a bounded quantity, but this quantity, I know it. When this goes to zero, it goes to zero. So similarly, I'll be able to come up with a posteriori estimate. These are computable quantities. So the same theory that I've discussed in brief will help you to do this. Now, see, everything seems to be very fine. So if I take practical problems here, so this turns out to be a framework of a problem where the advection, diffusion, advection, reaction term, everything seems to be very nice. Now we know that typical in this problem, two important parameters play a role. One is a Peclet number, other is a reaction number. Peclet number is the fight between the two forces. The first force, the advection force, the other one is the diffusion force. When two forces are fighting, whoever is leading, then that's going to dominate. If diffusion is, if advection is dominating, then Peclet is more. For if reaction and if diffusion is dominating, then Peclet is less. Similarly, if the reaction is dominating over the diffusion, then reaction number is more. Now, practically, I will have problems with large Peclet and large reaction numbers, and may also I have a situation where I have small Peclet and small reaction numbers. So, well-posed problem for which good solution exists. Everything seems to be fine. Will it work? Always nice. Let's see. If I increase my advection from, say, this is the velocity, 2, 1, 21, this is the U component, V component, to gradually keep increasing my velocity, my method for which I have known well-posed as excessive solution and convergence, everything, I talked a lot of things, it fails. It gives spurious oscillations in the solution. What is the problem? If I want to get the solution, I have to go to very high resolution, which becomes extremely costly by what I talked. So I need to now knock out. These has come out because of my numerical treatment. I have to introduce these spurious oscillations to knock out these spurious oscillations. I have to introduce what are known as stabilizations. So the same thing happens if we were to increase the reaction number. I don't have time. So there are stabilization approaches. This is coming because of the way I've introduced the numerical schemes. Some of the standard stabilizations are SUPG, GLS, and here we have subgrid multiscale approach, which is what I'm going to give a quick idea about it. This is essentially required for knocking out or cutting out these spurious or getting a good solution like this, even for very large Peclet numbers and large reaction numbers. So the idea of the subgrid multiscale method is now I'm going to look at my problem in two scales. One is resolvable scale, other one is unresolvable scale. In other words, the unresolvable scale we are going to deal with. For that, we introduce subgrid scales. Resolvable scales are regular scales, regular Galerkin finite element approach. Subgrid scales, we are going to introduce stabilized approaches. That means we are going to enrich our solution spaces by the subgrid scale spaces. So I get a new scale space. So that means our solution has got two components. One is going to be computed in the resolvable scale. Other one is going to be computed in the unresolvable scale. So if it now this is how the solution variable would look like. If we were to take this into consideration, you have an enriched space. In the enriched space, even a small problem would look like this. The 2D problem that I have, actually in the resolvable scale, it was only one problem, but in the enriched space, it turns out to be solving the resolvable scale and unresolvable scale. So they have a problem for resolvable scale and the unresolvable scale. Now this complexifies the problem. The original idea of moving from differential equation to weak form is now beaten. But then how to do with this? What we try to do is we will try to find the ways to express the unresolvable components in terms of the resolvable components through these governing models which we have derived now. So if you were to do we use the here basically we use the green function theory, and we go on successfully getting an expression for this unresolvable term in terms of the resolvable terms, and we get an expression for that. And if we rewrite the given problem turns out to be this. So we had original resolvable bilinear form plus enrichment as brought in some stabilization term. So this is the new bilinear form. So the new under the new bilinear form, in the compactification notation looks like bilinear form because the bounded linear form here I have, but this bilinear form I have the resolvable and unresolvable components coming into the picture. And the right hand side also we have resolvable bounded linear and unresolvable bounded linear. So that in this framework, I have dealt with all the resolvable, unresolvable components and put it back in the same old framework. Now for this, I have to prove again that this is going to lead to a solution which converges, and it is going to, for which I can get error estimates a priori and a posteriori. So this is the a priori estimate and the a posteriori estimate. I don't have time to go into the results. We get a good result. There are no oscillations. We counter it. We get the order of convergence as 2 nearly by our stabilized formulation. Now let me take you quickly into a few couple of minutes on the important Darcy-Stokes problem, because I have already established the line of entire methodology for getting to that. So let's say the computational model in this case would be something like this. I have a vector problem, which is essentially a Darcy-Stokes problem. Here's a Darcy term, that's a Stokes term, there's a time-dependent term, and I have a drug which is being transported. C is the transit pollutant. I have a coupling between these two. I can have this velocity term, this viscosity term may be dependent on the drug term. So I have a coupling between the transport equation, which again is a nonlinear term, and this mu, which is a viscosity term, that can be a nonlinear term, and that's in fact establishing a coupling between the transport of the drug and the Dorsey-Stokes problem. So for this particular model, now I'm in a system of equations coupling between the advection transport equation and transportation model. So this model, once again, I can get back to my subgrid multi-scale approach. I skip the details. I have to choose appropriate spaces. We will be, and I also do the time discretization apart from the space discretization. In this case, we, once again, if you do the space and the time discretization both, that means you do the spatial discretization in terms of resolvable spaces and unresolvable spaces, and you do the time evolution by using the popular time schemes like backward Euler or Crank-Nicolson, so on and so forth, you will get a completely discrete scheme of this kind. So which is now an algebraic model now, for which we can now show that we can, this, whatever we got, in fact, this is going to converge. You can derive the a priori error estimates for this model, and we will also be able to derive a posteriori estimates, which we have done it. So by, in this case, Lax-Milgram will not work. We have used several different approaches like semigroup theory, Ferrero-Galerkin approach, and fixed point theory in proving the existence uniqueness, and in deriving this, we have used Sobolev spaces for getting into deriving these a priori and a posteriori estimates. Now, what does this say? Now, whatever you talk, the scheme, subgrid finite element scheme that we develop works because as h and dt goes to 0, the error goes to 0. What is the size of this error? My a posteriori estimate gives the size of this error. So I will be able to get a bound on this. This is the subgrid multi-scale method which we have successfully developed and which is useful for the practical problems which I have shown. These are some instances of testing our model. I think I will not get into the details. We have again got a good convergence. Order of convergence is 2, and we get reasonable accuracy is 10 to the minus 4, minus 5, and order of convergence always remains 2. This is something which is good, which otherwise for large Peclet numbers and large reaction numbers, our method works fine. So this is a good contribution that we have made, and here we have made order of convergence plot, so on and so forth. So these are some references. So in essence, in the conclusion, I would like to say that we have introduced a very important model, which right in the beginning I've shown, which, sorry, I will show this slide, right? And then before I'm talking, this slide will be important. This is a problem where we have a flow of the blood and there's an occlusion and we're sending a drug, is supposed to diffuse out. How do we model the drug getting transported through this layer or arterial wall into this? That's the Dorsey model here. And we have the drug being transported. That's what exactly these equations are doing. And we have come up with a method which successfully handles in this scenario. We are in a situation now, we will be able to handle this problem in realistic scenario. In a academic scenario, our model works very well. Now we would like to actually work with the realistic geometries. That's where exactly we are placed. And with that, I would conclude. Thank you once again for giving me this opportunity. So I will put back the conclusions here. And thanks to the Kolkata, to the society for inviting me to deliver this talk. It is an honor to speak in this plenary session in memory of Professor Dr. N.R. Sen. Thank you very much.
Thank you, Professor Ratish Kumar, for your nice presentation. Since we are running out of time and there are 3 parallel sessions about to begin, so we are not going to the question session. With a brief introduction of Professor N.R. Sen, with a great photograph, Professor Ratish Kumar began his talk, and he beautifully explained a priori and a posteriori error estimations in energy norms, which may be used for well-known daily life problems like drug transmission in the blood flow and transport of pollutants in the groundwater, which is primarily based on Stokes model. This was a nice presentation, beautifully explained everything. Thank you again to Professor Ratish Kumar.
Thank you, madam. Thank you very much.
And over to Dr. Kaushik Ghosh
Thank you very much. Yeah. And thank you, Professor Kajol De, and thanks to Professor Atish Kumar for wonderfully conducting this session. So we end today's main program, and next we will be moving to the three different parallel sessions. And if you just go through this particular chat box, you will find out that I have already shared these particular links. This one will be for the 3A, and the 3B and 3C sessions will have these particular links. So please join accordingly. As you were having the interest, you have already go through this particular slides where you can find out different paper presentation details. So accordingly, you may join. Thank you very much. So we will meet again in the main session tomorrow at 4 o'clock. And in between, to just enjoy the different parallel sessions. Thank you.
Kaushik, can I start the session?
The fused images with machine learning tapping the smallest possible information to provide a better support in the line of treatment.
Something is going on.
Okay.
So this particular session will be chaired by Dr. Molar Banerjee. He is a convener of this conference. He is a faculty member of IIT Kanpur and also council member of Calcutta Mathematical Society. I would like to request Dr. Banerjee to take the chair and start the session. Please.
Thank you, Bablu, for kind introduction. And without any further delay, let us start the session. So in this session, we have 9 presentation. So first presentation will be delivered by Ravi Kumar Shailesh Kumar Shah.
Yes, sir.
Okay.
Yes, sir.
So you please share your slide, and because you know we are running behind the time. So
Yes, sir.
Within 5 minutes, you just describe your problem and what you have done, and then we can have 2 to 3 minutes to have some discussion if any question from the audience. Okay.
Okay,
Please.
sir. Good evening to all of you. Myself Ravi Shah, from research scholar from CVM University. Today I am talking about review on group theoretic transformation techniques on MHD boundary layer flow for non-Newtonian fluids. First of all, we see about here abstract. So in this paper, we summarize current progress on using the observed MHD boundary layer flow and non-Newtonian fluids on the stretching surface. The present review is intended to encompass and the application of some symmetry-based approaches for solving non-Newtonian fluid problems in various physical situations, and the obtain the ordinary differential equations are solved by various numerical methods and MATLAB softwares. In this review, I have tried to possible all articles published until 2021. So keywords are MHD flow, group theoretic method, numerical methods, and MATLAB softwares. So first of all, your introduction. MHD flow, there has been considerable focus in the study of the physical behavior and project properties of non-Newtonian fluids over the past several decades. One particular reason for this interest is the wide range of application of such models both natural and industrial, it is essential to study the principal characteristic and parameter of fluid flow, which is addressed by the subject fluid mechanics. What is the similarity transformation? In a physical problem, in engineering science are often described by differential model, either linear or non-linear. In similarity transformation, the direct as well as group theoretic method are applied to non-linear boundary value problem arising in engineering science. There are so many different group theoretic method, one parameter group theoretic method, two parameter group theoretic method, characteristic function, etc. MHD boundary, what is the MHD boundary layer flow? The fundamental concept behind the MHD is that a magnetic field can induce the current in moving the conductive fluid, which is a turn polarize the fluid and reciprocally change the magnetic field itself. Stretching surface is a stationary cooling fluid. In a main stage is in a lot of manufacturing processes such as a plastic sheets, glass manufacturing, etc. Basic difference between the fluid and heat mass transfer, faster stretching and sinking sheet at different type of sinking velocities are considered. The purpose of this review is that to present this review is to deliver a detailed analysis of those studies which deal with the fluid models of non-Newtonian fluids and solving using by the group theoretic approaches. I have presented the historical background of each of the objective under review together, and I have in this review I have used by 53 total papers. The main objective, the first objective to study effectiveness and significance of transformation method to analyze the engineering boundary value problem, to study effect of different physical parameters on fluid flow for the Newtonian and non-Newtonian fluid model, to study the transformation of non-linear boundary value problem to linear boundary value problem, to study utilization of simple and powerful techniques called as a group theoretic method to convert boundary value problem to initial value problem, to study a non-similarity solution when similar solutions are not possible, and to study the numerical solution of converted ordinary differential equation by applying numerical methods and by using computer softwares. So now a review of papers. So I make a table by objective wise. So first objective is to study effectivity and significance of transformation methods to analyze engineering boundary value problem. So different author in different years using by different geometries and different fluid flow by using a different model and obtain a different result. I have shown in that I was make a table from different authors. So continuing this objective, the second objective to study effect of different physical parameter on fluid flow for the non-Newtonian and Newtonian fluid model. So in this objective, different author in different year by using a different geometry and a different fluid and they use the different model to use and they obtain the different results. So same objective is to continue. The third objective to study the transformation of non-linear boundary value problem to linear boundary value problem. In this objective, different author use a different geometry and fluid model, and they use a different model and they obtain the result to non-linear boundary value problem to linear boundary value problem. So this continue. The fourth objective to study utilization of simple and powerful technique called as a group theoretic method to convert boundary value problem to initial value problem. In this objective, different author in different year use a different geometry and fluid and the model, and they obtain the result to convert the boundary value problem to initial value problem. To study a non-similarity solution when similar solutions are not possible. On this objective, different author has been work done on a different year using by different geometry and different fluid model, and they obtain the result to a non-similar solution. The last objective to study the numerical solution of converted ordinary differential equation by applying the numerical method and by using the computer software. On this objective, different author has been work done in different year by using different geometry and different fluid model, and they obtain a ordinary differential equation and is solved by numerically different method and by using a MATLAB software. So discussion, I have shown here a graph in bar chart from a published paper growth during the last 10 years. In 2013, 17 and 2021, so many work has been done on this group theoretic method on MHD flow. And second graph is show here to publish a paper contribution by different publisher. So here the name of the publisher and the number of papers who have published by different publishers. So now conclusion, studies related to the flow models of different non-Newtonian flow and group theoretic transformation techniques are discussed in this review. Numerical methods like shooting method, homotopy method, boundary shape function method, finite difference method, etc. are used for the solution of converted ordinary differential equation. Some problem is also solved numerically by MATLAB software. The aim of this review is helping the researcher to understand the different aspects of group transformation theoretic methods. This method is useful to engineers and scientists. It is important to conclude that more studies areas is required for serving not only for engineering and scientists but also our societies. The suggestion of the future work: presenting new models of MHD flow in stretching surface, exploring the physical mechanism behind the model of MHD flow problem, investigating the impact of different geometries and properties of MHD flow on stretching or sinking sheets. Experimental studies on different geometries and the flow regimes can be performed on MHD flow. Most of studies done with numerical methods. It is necessary to obtain exact solution of such type of flow problem. There is a field of research that need a more analytical and experimental studies to know better hydrodynamics properties. So there are some references that I have used to make this review paper. Total 53 paper I have used. So thank you.
Thank you very much, Dr. Shah. Any quick question from the audience? If you want to have any further details from Dr. Shah.
Yes, sir.
Yeah, please. Anyone like to ask any question? Okay, so thank you, Dr. Shah. Thank you for your presentation. Our next presenter is Tejas Kumar Sharma. Tejas, are you here? Tejas Kumar Sharma. I think he is not present. Okay, so let us move to the next. Yeah,
I am present, sir.
Oh, sorry. Oh, sorry. So our next speaker for this session is Dr. Tejas Kumar Sharma. So please.
I am audible.
Yeah,
I am audible, sir.
You are audible. Please share your screen.
Yes.
And
is it visible?
Yes.
Good evening to all of you. May I start, sir?
Sure.
Good evening to all of you. I am Tejas Kumar Sharma, research scholar from CVM University, Anand, Gujarat. Here I represent the review paper on application of numerical method in fluid flow through porous medium. First, content of the presentation includes abstract, introduction, review papers, conclusion, and references. We start with abstract. In this paper, we examine the work done in area of porous media and related mathematical models. Also study different phenomena like instability phenomena, infiltration phenomena, fingering phenomenon, imbibition phenomenon. Also, numerical and analytic methods such as finite difference method, homotopy analysis method are used to solve partial differential equation which occurs after mathematical formulation of the model. Also, we learn that numerical calculation and graphical interpretation, different mathematical tools like MATLAB software, mathematical software are used. This study helps researchers to find a research gap for future aspects. Next, introduction. Porous media. Then, what is the porous media? A porous media is a material containing pores which is typically filled by fluid like water, oil, gases. the skeleton portion of the material called matrix. Porous media include many man-made as well as natural materials. In porous media, porosity, permeability, and the Darcy's law play a crucial role and important property. Darcy's law established the fundamental microscopic relationship and helped to formulate partial differential equations to control groundwater. Mathematical models help to explain system, study the effect, and make prediction about the behavior. Soil, sand, cement, limestone, foam rubber are different. The are examples of porous media. Here is the figure we present example of porous media. Next. Here I take some review papers to review the paper. Start with first paper. R. Mayer and others discuss the theoretical models of moisture content in one-dimensional fluid flow through porous media, adopt decomposition method and mathematical software used for finding numerical solution and graphical representation. Next one is A.K. Parikh and M.N. Mehta and V.H. Pradhan is focused on the solution of Fokker-Planck equation in unsaturated porous media. Similarity transformation is used to reduce the nonlinear differential equation in Abel's equation of second type. Analytic solutions obtained in terms of transcendental function. Ravi Borana and others focus on one-dimensional infiltration through unsaturated porous media. Craig-Nicolson finite difference method used to obtain solution of the Bose equation. Graphical representation is obtained using MATLAB software. Piyush Mistry and others discuss analytics solution of fingering phenomenon in double phase flow through porous media. Mathematical software and variational iteration method used to solve to obtain approximate solution of governing equation. As a result, we conclude that variational iteration method is easy, truthful, and effective compared to other analytic methods. Taylor, Kruti, and others discuss approximate solution of one-dimensional groundwater flow recharge problem through porous media with parabolic permeability. Again, variational iteration method used for formulate the phenomena which creates sequence which help to find exact solution. Again, mathematical software used for obtaining nonlinear solution of nonlinear partial differential equation. Srikanth Pathak and others discuss solution of analysis of groundwater flow using mathematical model in implied porous media. Lupit's assumption is used to formulate the groundwater recharge problem. Numerical and graphical representation is obtained by using mathematical software method. Kajal Mehta, Kajal Patel, M.N. Mehta and Twinkle R. Singh discuss the homotopy analysis method application in instability phenomena. Numerical solution and graphical interpretation obtained using Maple software. Ravi Borana and others focus on solution of Burgers equation arising in longitudinal dispersion phenomena. Crank-Nicolson finite difference method used to solve partial differential equation. And which focus on theoretical model in instability phenomenon in double phase flow through homogeneous porous media. Also discuss the problem of fingering phenomenon in porous media with capillary pressure in statistical point of view. This plain finite element method used to solve nonlinear second order partial differential equation. Vikrant Pathak and others focus on analytic solution of mathematical model of Mosaic equation, homotopy, homotopy analysis method used to solve the equation, governing equation, and Mathematica software is used. We omit one and start other. Deepak J. Patel and others discuss the problem related to fingering phenomenon in invisible fluid flow through porous medium and its mathematical model. Basic optimal homotopy analysis method used to obtain solution of the equation. Again, Mathematica software used for numerical as well as graphic representation of the solution. Mahendra Patel and others focus on spontaneous imbibition through porous media. Mathematical model is developed for co-current imbibition phenomenon in homogeneous porous media. The solution of governing equation obtained by homotopy analysis method and is interpreted by graphically. Deepak Prajapati and others focus on counter-current imbibition phenomenon during secondary oil secondary recovery process. Homotopy analysis method used to find approximate analysis solution. Mathematica software used for graphical interpretation. And we omit one more paper and next Srikanth Pathak and Twinkle Singh focus on approximate homotopy series solution of imbibition phenomenon occurring in multi-phase flow during the secondary oil recovery process. Optimal homotopy analysis method used to solve governing differential equation. Last paper. Dr. K. Sivasandra and others discussed the longitudinal dispersion phenomena of one-dimensional concentration distribution in visible fluid flow through homogeneous porous media in terms of adequation dispersion equation. To solve this, Duhamel's theorem, Laplace transform, and moving coordinates used. Solution obtained is in terms of exponential form as well as in complementary error function. These are some reviewed paper, and from this reviewed paper, we conclude. Sorry, sir. Sorry. Am I audible? Hello.
Yes, you're audible. Please.
From the review paper, we conclude that this review helps researchers to become aware about the work done in the area of porous media and related mathematical models. Also, we conclude that researchers have worked on one-dimensional mathematical models. So, in future, there is a possibility to extend the model in two-dimensional space variable. Also, in future, we add latest approach into numerical methods for more efficiency so that one can get better results. These are the references we use. Thank you.
Thank you. Thank you, Dr. Sharma. I have just one question that what is the main journals you have concerned to prepare this review article?
Sir, I read different papers.
Yeah, but the point is that I can't see the work of some of the leading people even in India, for example, by Somnath Bhattacharya, Partho Gopmandal. They have this work in porous media, and papers are published in journals like Journal of Fluid Mechanics, Physics of Fluids, but those are not covered by you. So my suggestion is that you can have a look at their publication, and those are quite up to date and very advanced level work that you should consider. Okay.
Thank you, and thank you, sir, for suggestion.
Yeah, thank you. So our next speaker is Sumit Shobhan Sardar.
Yes, sir.
Yeah, Sumit, so please share your screen and start your presentation.
Okay.
And please try to be conclude within 7 to 8 minutes because you know we are running behind the time.
Okay. I'll try my best. Hello, good evening, everyone. My name is Sumit Shobhan Sardar, and the title of my talk is Modeling of Three-Dimensional Anisotropic Half Space using Multi-Phase Lag Model. So here's the abstract. So in this work, we generalized thermoelasticity theory is applied to an anisotropic half space medium under the heat equation with multi-phase lag model subject to mechanical and thermal loads at its boundary surface. A vector matrix differential equation is obtained by using normal mode analysis from the governing equations, which is solved by the eigenvalue method to obtain the analytical closed form solution for the displacement components and temperature distribution. At last, graphical illustration of the effect of the field variables and stress components are done under the change of several physical parameters. So in introduction, as a background of our research work has been discussed. So I'll say try to say it briefly because we due to lack of time. So for last several decades, it has been seen that non-isothermal problems in the theory of elasticity has become very popular, but thermoelasticity theory is more effective because it deals with the direct and inverse impact of heat on the elastic medium due to deformation. So both uncoupled theory and coupled theory are used to solve problems, but Biot proposed a theory of coupled thermoelasticity to overcome the paradox of infinite propagation of heat wave in classical thermoelasticity. Besides this, there are other thermoelasticity theory also, like LS model, which was proposed by Lord and Schulman, and GL model, which was proposed by Green and Lindsay, and there is GN model, which was proposed by Green and Nagdi, etc. So without delaying much, I come straight to our problem. Where, so here we have investigated a thermoelastic anisotropic medium in context of refined multiphase lag theory, which was earlier investigated by Zenkor. Here we tried to make generalization of phase lag variables, and also we have shown special cases drawn from the refined multiphase lag theory model. So here how the formulation of the problem is done. So in the orthogonal coordinate system xi, we consider three-dimensional anisotropic half space defined in the region omega given by this, subject to fraction free boundary x1 is equal to 0. Here x1 axis is taken vertically downwards, so the region of consideration is the lower portion of the x2 x3 plane. We may assume without any loss of generality that the propagation of waves along x1 direction and as such field variables are functions of the space variables x1, x2, x3 and time only. Also, the temperature field is also function of the space variables and time only. Assuming that a body having mass density rho is in unstressed and undeformed state at the constant reference temperature θ0, the body undergoes deformation.
Dr. Sardar, sorry to interrupt you. Instead of reading this text line by line, you just go to the problem, explain, and then conclude the final conclusion.
Okay. I'm not reading everything line by line. I'm skipping much things. I'm just telling those important things. Okay. So deformation Ui and respective temperature increment acquired theta minus theta 0. So the absolute temperature theta is chosen such that this the modulus of theta minus theta 0 and divided by theta 0 is very less than 1. So in the absence of body force and heat source, the equation of motions are given here by equation 1, and the heat conduction equation in multi-phase lag model is given by the equation 2. The stress strain temperature relations are given by equation 3. Now using Hooke's law, the stress strain temperature relations are given by the equation 4. Now using this equation 4, we obtain from this the equation 1 the equations 5, 6 and 7. These are the transformed equations of the governing equations, the equations of motions, and the heat conduction equation in multi-phase lag model is given by this equation. Now, to transform the equations, the governing equations, in the non-dimensional form, we use the following non-dimensional variables, which are given by this. Now, using the non-dimensional variables, we obtain from the transformed equation of motions, we obtain these equations, equations 10, 11, and 12. These are the equation of motions after using the non-dimensional variables. Now, here we omitted the primes for convenience, and the multi-phase lag heat conduction equation becomes this, which is given by equation 13. And here also we have omitted the primes, and we have introduced the non-dimensional variables here also. And also the stress components becomes this, which is given by the equation 14, and so these are the stress components. Okay, now here comes the method of solution. So here we applied vector metric differential equation, like I said earlier. So to obtain the vector matrix differential equation, one can use Laplace integral transforms like Laplace and Fourier transforms, but here we have used normal mode analysis, and we obtain the following equations 16, 17, and 18 after undergoing this normal mode analysis. And so 16, 17, 18 are the equation of motions after applying the normal mode analysis. And after undergoing the normal mode analysis, the heat conduction equation becomes this, which is given by equation 19. And the stress components are given by equation 20 after using the normal mode. So using the equations 16, 17, and 18, we obtained the vector matrix differential equation, which is given by dv dx1 is equal to av, where v is the column vector given by this. u1, u2, u3 are the displacement and theta temperature, and these are their derivative. And here is a 8 by 8 matrix A, which is called vector matrix, which is divided into 4 equal blocks, 4 by 4 blocks, where L11 and L11 is the null matrix of order 4, L12 is the identity matrix of order 4, and L21 and L22, these two blocks are given in the end at appendix A. Now, solution of the vector matrix differential equation is done in this way. So we first solve the characteristic equation given by equation 22 and find the eigenvalues, which eventually be of the form of this, and the eigenvector is given by this for a eigenvalue lambda. Now we apply the boundary conditions for this problem, where we have considered the half space in the region given by R. To determine arbitrary constants, we consider the following two boundary conditions are prescribed as follows. So we have considered two cases. One is mechanical boundary condition. Here we consider the traction-free boundary surface of the half space x1 is equal to 0. Here all the stress components are considered to be 0, and here is the thermal boundary condition. And in case 2, we consider the traction-free boundary surface of the half space where x1 is equal to 0, but here the normal stress component tau11 is considered to be sigma 0, and other two sharing stress components tau12 and tau13 is considered to be 0. So for numerical analysis, we performed by considering two different sets of boundary conditions. To study the nature of characteristic curves, we considered the following physical conditions in triclinic half space, as in Chattopadhyay and Rogerson. It's given in the references also. So these are the value we have considered for elastic moduli, and here the density and other things are, other values are considered. So here are some graphs has been portrayed here. We have considered the behavior of normal space components tau11 with respect to the space variable x1. Here the sharing trace components tau12 has been shown with respect to x1.
Could you please quickly conclude?
Yes. Yes.
Could you please quickly conclude?
Yes, yes, I can quickly conclude. So these are the graphs with respect to several space, the behavior of temperature and displacement with respect to several space variables. And here is a table, two tables are shown where the stress components and displacements and temperature are shown with respect to different thermoelastic models. And so in conclusion, I can say that the thermomechanical analysis of the anisotrophic half space has been investigated applying two temperature parameters with modified coupled stress as the extension of the study by Zhou, who actually introduced that coupled thermoelasticity theory. The concept of multiphase-like thermoelasticity has been established and verified here successfully. The characteristic behaviors of defined components of stress, displacement, and temperature with respect to several thermoelasticity model, which are given in the table also, has been represented analytically and graphically. I've shown the graphs. The validity and accuracy of this study has been assured through the boundary condition provided in two different cases. So these are some references we have used. And thank you for your kind attention.
Thank you very much, Dr. Sardar. And due to time constraint, I am not going to take any question. Thank you very much for your presentation. So our next speaker is Mohammad Najimul Islam.
Yes, sir. I am present.
Yeah. So please share your screen and try to finish your talk by 7 to 8 minutes at most. Okay.
Yes, sir. Okay, sir. Good morning, everyone. Myself, Mohammed, a research.
Najimul, your slide is not loaded completely and you are not audible right now. Najimul, are you there? Najimul, can you hear me? Bablu, I think there is a problem with his
presentation.
presentation.
I think there is a network connection problem.
Network connection problem, and the file may be of huge size. That's why it is not loading properly.
He left.
Okay, so better we can move to next talk just to be make up the time. Okay.
Sure. If he rejoin, then you can give chance later.
Yeah.
Okay.
Yeah.
Please.
Dr. Satyajit Pal.
Yes, I'm here, sir.
Yeah. So you please present your talk.
Yeah, sure. Am I visible?
Yeah.
Good evening, everyone, and thank you for giving me the opportunity to present this paper in such a time.
There is lot of disturbance with your
Hello.
audio.
Hello, sir.
Mohammed, just
Hello,
wait
sir.
for some time. Just wait for some time. Next presentation is started. We will place you after this talk.
Yes, sir. Okay, sir.
Okay, please continue. But there is still some interference of the sound from surroundings.
I am trying to my best. There is a problem. The presentation is model of COVID-19 scenario. This is a joint paper. This is and Dr. Sudipta Seshina, professor of Rajah College. Here is the outlines of my presentation, and the main objective of this paper are to build a mathematical model of COVID-19 infected cases in West Bengal to focus on district-wise distribution of number of infected cases of this fatal virus and come up with a model to predict the future situation of COVID-19 infected cases and assist to take preventive measures in the application. We have, for this paper, we have basically collected the data within the time period 1st May 2020 to 1st December 2021 and fitted with the polynomial with degree 2, 3, and 4. Also calculated the values of R square, which are given in the table. We also, and after that, we observed that the 4th degree polynomial fits the data well and provides the weighted value of R square. And also notice from the curves we have drawn in the graph that each curve has 3 major turnings. That's why we have chosen the 4th degree polynomial for this model, which are given by this, and the error may be defined by this. To calculate the error, we have used multivariate calculus, and correspondingly leads to this equation, and the corresponding normal equations are these. After minimizing the error, the 4th degree fitted polynomial will look like this. To check the quality of this model and the goodness of it, we also calculated the values of R square and adjusted R square, which are given by these equations. And we have collected the data from GitHub and COVID-19 India and used the software Python and Microsoft Office Excel to draw the graphs and analyze these graphs. The monthly data of infected cases of some districts of West Bengal are shown in this table. We are not able to provide all the data of all the districts of West Bengal due to lack of space. Here the column diagram representing the number of infected cases of all districts of West Bengal. And observing this diagram, we easily see that the number of infected cases in Calcutta and North 24 Parganas are significantly high, whereas the number of infected cases in Kalimpong, Jhargram, and Alipurduar are quite low. Throughout this context, we have considered 5 most effective districts of West Bengal, which are North 24 Parganas, Kolkata, South 24 Parganas, Howrah, and Hubli. And the empirical equation for these 5 mentioned districts are given by this. If we draw the graph of these equations, then the graph will look like this, where the blue line indicates the observed data and the black line indicates the estimated data. And we have considered the number of infected as the y-axis, also the number of months as the x-axis. And if we observe the data graphs, we see that the number of infected was quite low after 3 months, and after that it started to increase. And again, after 9 this is a slow down, and again after 12 months it started to increase exponentially during the second wave, which ensures that the second wave is much heavier than the first one. We have also calculated the values of R-square and adjusted R-square for the 5 districts, and these values ensure that our model is very good. Instantaneous rate of change. Basically, this is a very useful parameter to estimate the future spreading of this spectral patterns. It is also utilized to predict the rate of these patterns at a particular time. And it is obtained from derivative obtained from differentiating the different polynomial, which is given by this. Also, the IROC of these 5 mentioned districts are obtained from equations, and if we represent this equation graphically, then it will look like this, where the rapid increasing of the IROC value indicates the uncontrolled spreading of the COVID-19 viruses, which might be from the animal to the human being, and the negative values of COVID IROC values, negative IROC values indicates the decreasing tendency month by month. And the analysis of these graphs are in our main paper. Here I am giving time. I am saving this portion, and the effectiveness is this paper will be very much effective if further waves of these finals outspread in coming days. It's also really useful for the such a pandemic situation like COVID-19 in near future. And these are the references in this paper. And thank you again for such an opportunity.
Thank you very much, Satyajit, for finishing your talk within stipulated time. Thank you very much. And without any question, let us move to the next talk. So, thank you very much. Mohammad Najimul, could you please present now?
Yes, sir. I am present, sir.
Yeah, please start your presentation.
Yes, sir. Is my screen visible, sir? Hello?
No.
Is my screen visible, sir?
Yes.
Okay, sir. Good morning, everyone. Myself, Muhammad Najimul Islam, a research scholar from Ali University, under the supervision of Dr. Ibrul Kayes, sir. I am going to present my paper entitled with fractal functions on base of spaces. Now, I move on to the introduction and definition part. The theory of fractal function is comparatively new in mathematical science, So it is so important to know what a fractal function is. To know this, first we need to know about fractal functions. Due to Benoit v. Mandelbrot, we can say that a fractal is a rough or irregular or zigzag-shaped geometric structure that can be subdivided in similar parts, each of which at least approximately a reduced shape-similar copy of the entire. This is Sierpinski triangle, a fractal, man-made fractal, because it contains self-similar parts. Even if you have to zoom in repeatedly many and many times as you like. Mandelbrot said, and the Koch car, lightning, Julia said, and the branches of trees are also the example of fractals. Now, in the sense of fractal concept and due to Maria Navascu, we can also say that a fractal function is nothing but a special type of continuous function defined on a compact interval of real line which interpolates a certain data set and whose graph is of fractal structure. These are the examples of fractal function. First one is the graph of a financial series, and second one is the graph of Weierstrass function. Next, we want to discuss about mathematical approach of fractal function. Navascu constructed alpha fractal function as a fractal analogous corresponding to a continuous function in the following way. Let f be any continuous function and delta is a partition of the compact interval I, dividing the entire interval I into n number sub-interval II, matching with the partition delta. We can apply n number affine maps LIX equal to AIX plus EI, enjoying the condition, join-up condition 2. If the continuous function B, that agree with the original function f, whose factorization we want to do at the end points of the interval I, and if the vector alpha 1, alpha 2, alpha n satisfy the condition that the maximum of mod of alpha I is less than 1, then it is not difficult to show that the RB operator defined by the equation 3 is a contraction on the space of all continuous function CIA, which is also a complete metric space with respect to uniform norm. And hence, Banach fixed point theorem ensures that T has a unique fixed point f alpha that obey the self-referential equation 4. This is the function f alpha. This function f alpha is called alpha fractal function with the base function b. Each alpha I in equation 4 is called scale factor, and the corresponding vector alpha 1, alpha 2, alpha n is called scale vector. A detailed discussion of the theory and application of alpha fractal functions can be found in the literatures, which I have mentioned in the reference section. In this paper, mainly we have shown that the alpha fractal function of any function taken from base of space exists under some suitable condition. So now we go straight to our main section, that is the existence of alpha fractal function on base of space. But we need to know about base of space first. For this, the nth order difference operator delta RH of positive step h acting on a function f is given by the relation phi. The base of space is the collection of all functions for which the quantity given by the equation 6 is finite. If If the reals P and Q lie between 1 and infinity, then the quantity defined by the equation 6 is a norm, and hence base of space becomes a Banach space. Now I am drawing everyone attention to our main result, that is theorem 2, in which the existence of alpha fractal function of base of function is shown. In this theorem, we take a function f from base of space where the conditions in 7 are satisfied. If the base function b and the scale factors alpha I satisfy the condition 8, 9 and 10 for the different values of p and q, then we have succeeded in showing that the RB operator t, which is defined on the space, base of space, and also defined by the equation 11, is contraction. Furthermore, P has a unique fixed point f alpha that obeys the self-referential equation 12. This is the function f alpha that we call alpha fractal function corresponding to the function f taken from base of space. This is a figure with the classical function fx equal to root x, and that is the graph of our classical parabola on the left figure, and on the right the corresponding fractalization of that parabola, that is a fractal parabola. If you zoom in, no matter how much on any portion of this fractal parabola, the similar zigzag figure will appear repeatedly. Next, references. These are the references we use to establish our complete work. This completes the presentation. Thank you very much for your nice attention.
Thank you, Mohammad Najimul Islam, for very nice and precise presentation. And you know that all of us are actually running behind time, so quickly we move to the next presentation. Thank you very much for your nice presentation. So our next speaker is
presentation, sir.
Yeah, please you stop sharing your screen here.
Yes, okay, sir.
Okay, so our next speaker is Chandrali Boisho. Chandrali,
yes,
please
can
share
you hear
your
me, sir?
Yeah, you're audible. So please share your screen and try to complete your lecture by 7 to 8 minutes.
Yes, sir.
Hello.
Can you view my screen, sir?
No. Now it is visible. Yeah.
Yeah. Thank you. Good evening, everyone. I am Dr. Chandrali Boisho from Tumakuru University, Karnataka. My topic of presentation is a new operational matrix of integral differentiation for Atangana-Baleno fractional derivative. So in this presentation, we have derived an operational matrix using the Legore polynomial to solve the differential equation involving Atangana-Baleno fractional derivative, and this operational matrix is of fractional integration and fractional integral differentiation. So using the that operational matrix and the collocation points, we have converted the fractional differential equation to a linear or nonlinear algebraic equation, and the error bound is also derived for the particular operational matrix, particular technique. To illustrate the accuracy and the reliability of the projected algorithm, numerical simulation is presented. Also, we have compared the results obtained by the projected method and the already available results in the literature. So as a brief introduction, we have solved the equation of the type this multi-order fractional derivative of the type 1 by using where initial value problem with initial condition of the integer order derivative. So this is what is the main form of the equation. So overall, this is what the outline of the presentation. So first we are going to show the functional approximation of by Legare polynomial, then the Atangana-Boleno derivative operational matrix of integration, then integral differentiation and the convergence analysis, and finally the method of solution. So here are some preliminaries. So like just I will quickly go to glance through this all the things, and mainly we are using the this is what the derivative definition definition 1 for Atangana-Boleno derivative, and here this is what the derivative for the polynomial function. So this is what the definition is. This is defined for any value of alpha, like from in the limit interval n and n plus 1, and the corresponding integration formula is this one, and the integration of the polynomial function is this one, but the interesting part is what is the integration of Atangana-Boleno fractional integration is defined only in the limit when the alpha lies between 0 to 1, but using our method, operational matrix, we have derived in such a way that it can be used for any limit of integration. That means even if alpha lies between more than 1, like if the interval is more than 1 also, this method can be used. So this is the definition of Legare polynomial, and here is the orthogonal property of the Legare polynomial. Okay, so if given a function v of t, we consider as a series of Legare polynomial as summation of j equal to 0 to infinity ej Lj of t. Lj is already defined in the previous one. And then this one can be converted to the matrix form by using matrix form using this one. Okay, so here is the first one. What we have derived is for operational matrix of fractional integration, Atangana-Boleno fractional integration. So here is the method we have utilized. So Lj, that means this is the definition already I have given in the preliminary section. Alpha may be here, if the fractional derivative alpha may be an integer, alpha may be a non-integer, which can be more than 1 also. So in that case, we are going to separate the integer part and the integer part and the decimal part. And then we are going to use this Lj of t is integrated by Atangana-Boleno integration of order beta, where beta is the decimal part, that means between 0 to 1. Then this is what we get by using the formula, already defined formula. And here, then we integrate again n times. So when we integrate n times, only t raised to k plus b beta and t raised to k should be integrated. So since it is n time integration, even if it is more than 1 also, it can be done. And then by using the orthogonality property of Legare polynomial, we can write t raised to n plus k and t raised to n plus beta plus k in this form, and where the coefficients can be written in this form, like derived in this form. Once we substitute back to the equation, so we get the matrix of like this one, equation number 8. So then the integral differentiation, when we use the same way, we can do the same thing for the integration. So if alpha is equal to eta plus m and alpha is equal to beta plus n, this is what we can get the matrix as. So here is the derivation again for the whole thing. So that means whatever we got earlier, alpha z, that is differential, because our integration differential equation, that means fractional differential equation, may be having order more than 1. That means it could be 1.5, 2.5 in such way. That time we require this type of condition. Again, by differentiating the integrated part, we get in this form. So finally, we can derive the matrix of fractional integration. by using the same orthogonality property and the definition of integration, fractional integration. And error analysis is also performed, but I have not plotted the proof here because it's becoming very long. Okay, so this is what a method here we can explain. The difference, if alpha is from 0 to 1 or alpha is an integer, then we assume that the derivative part, fractional derivative part, as the series in terms of Lagrange polynomial, and then integrating on integration, it can be equation 11 can be obtained. So if alpha is from 0 to 1, then this part will be only one term. That means phi naught of phi of t naught. Otherwise, we have a summation terms like this, and this part can be written in terms of in matrix form as G naught transpose phi of t. And similarly, this one already the matrix is used, operational matrix is used, and this differentiating we can get various differentiation and substitute in the equation. Suppose alpha is here. 1 minute, yeah. So differentiating 11, we get that means suppose alpha is more, then what we'll do is we are going to take the small part, that whatever alpha is, that part we are going to take as the derivative part we are going to write in this form. And finally, we can get the residue equation, and by using the collocation point, we can get the system of equation. So now, so here, whether alpha is more than 1 or whether alpha is less than 1, so we can use for both type of Atangana-Boleno derivative, we can use this operational matrix of integration and operational matrix of integral differentiation. So we have in this paper, we have used the collocation point as I by n. N is the number of points we consider, or number of terms we consider in the series. Know that we can use different collocation point also and get the solution. So here are some examples I have considered. So this is the example, whereas v double dash, and this is the derivative term, fractional derivative terms, and we got like this. So in this case, so this one v double dash, which is actually integer derivative, so we consider as the series. Then since we consider this as the series, so we have the, so this term can be written as the series. That means this is the matrix form using operational matrix. Whereas when this is alpha is equal to 0.1, that means what it will be? It will be 2 minus 0.1. That integration matrix will be used here, and v of t will be used here. So using by computing different type or different matrix form, we are going to get G1, J alpha transpose, all these values, and finally v of t, the solution can be obtained in this manner. V of t is shown here, and this one we have found for n equal to 4 and n equal to 6, which we have compared with the existing result in the literature. So where it is used applied for 8, n equal to 8 and n equal to, in this paper 9, where it is not given what is the value of n is given, but still I have just given the result, showed result in that paper. So our result is like this. So when I took 4 and when we take n equal to 6, we got in this type of accuracy. Similarly, another problem, these are various...
Could you please quickly conclude?
Yes, sir, yeah. So we get, these are our various type of examples. Even we have taken third order problem also, and this is one the recursive equation where we have used the derived operational matrix. And another different problem we have taken when alpha is an arbitrary in the sense it is not mentioned here, and then for there also we got very good accuracy. Similarly, this is another problem we have taken where interestingly the exact solution itself is non-polynomial. In such cases also we got quite good accuracy using our present method. So overall, the present method what we have derived is can be considered as one of the efficient method to solve the fractional differential equation involving Atangana-Boleno capital sets. And these are few of the references where we have referred while deriving this method. Thank you, sir.
Yeah, thank you, Dr. Boisho, for your presentation and nice work. Okay, so thank you very
Shall I
much.
stop sharing, sir?
Yeah, sure, please.
Thank you, sir.
So without any question, we can move to the next talk. Next talk will be delivered by Dr. Ajoy Kumar.
Yes, sir.
Yeah, so please share your screen and start your presentation. Try to conclude within 7 to 8 minutes. Yeah,
sir, my screen is visible?
As of now, it is not visible, but...
Sir, now?
No. Yes, yes. Yeah, fine.
Okay, sir. Good evening, sir. My my topic is solution of quadratic integral equation by the homotopy analysis method, and I am belonging to Department of Mathematics, University of Rajasthan, Jaipur. Abstract. In this paper, we use homotopy analysis method to obtain approximate solution as series solution of quadratic integral equation. This method contains an auxiliary parameter, and this parameter control the convergence of series solution. We compare the approximate solution with the exact solution and displayed in two-dimensional graphs. There are using some keywords as quadratic integral equation, homotopy analysis method, nonlinear integral equation, and integration. integration uh, Quadratic integral equation is a particular form of a non-integral equation. It is very important and applicable equation in various fields such as science and engineering, mathematical, physics, and there are some any other fields. Due to time, I am skipping introduction. This is also introduction, and basic computational technique of HAM is this. First of all, we consider the quadratic integral equation as given in equation number 2.1, where n is nonlinear operator and xt is a known function and t is independent variable. And now consider the homotopy by traditional homotopy method, which is given in reference number 30 and in equation 2.2. Where p is belongs to 0 to p is belonging to between 0 to 1 is an embedding parameter, and there are some explanation in using variable in equation number 2.2. And thus as p increases from 0 to 1, the solution xtp varies from the initial guess x naught t to the solution xt by using Taylor series, expanding phi tp with respect to p, and phi tp is equals to in equation number 2.4, where xm t is equal to in equation number 2.5. The initial guess auxiliary linear operator h and auxiliary function are chosen properly, then the series 2.4 converges at p is equal to 1 as proved in reference number 30. And the final solution in the form of equation number 2.6 as xt is equal to this, which is solution of given integral equation by reference number 30 and equation number 2.22. This is using the homotopy in equation number 2.7, which is used in homotopy perturbation also reference number 22. Differentiating 2.2 m times with respect to p, and then setting p is equal to 0 and dividing by the m factorial, we have the mth order deformation equation as given 2.9 number equation. This is r the value of rm is this, which is given in equation number 2.10, and kappa m is equal to, when m is less than equal to 1, then this going to 0, and m is greater than 1, then kappa m is equal to 1. Main results we use in main results two examples in this section with some examples to quadratic integral equation which are solved by homotopy analysis method. First example, we take this quadratic integral equation 3.1, and initial the exact solution of 3.1 is xt is equal to t square. Now we applying HAM, it means homotopy analysis method, then uh, uh, the linear operator as in equation number 3.3 and nonlinear operator as 3.4. Now consider a homotopy for st is equal to 1, which is given in equation number 3.5. Thus we obtain the mth order deformation equation in 3.6, which is given in 3.6 number equation, where Rm is equals to is the value of Rm is given in equation number 3.7. By using 3.7, we have the value of Rm x m minus 1. For m is equal to 1, R1 x naught is this, which is equation number 3.8. For m is equal to 2, equation number 3.9. For m is belongs to n, it means m is a natural number but not equals to 1, then the value of Rm is in equation number 3.10. And for all natural number which is including also m is equal to 1, then the value of Rm x m minus 1 is equal to this in equation number 3.11. By using equation number 3.6, we have the value of xm, and taking initial condition is x naught is equal to x naught t is equal to t square minus t raised to power 10 upon 35. The initial condition can take freely. So if we put the value of xmt for m is equal to 1, 2, 3 and so on, as then we have the value of x1t is equal to this, which is equation number 3.14. x2 is equals to this is in equation number 3.15, and so on. We get x2, x3, x4 and so on. Finally, these x naught, x1 or x naught, x1 and x2 and so on, x3 put in equation number 2.6, then we get the value of xt. This is the approximate series solution. This is required to result, and if we put h is equal to -1 in equation number 3.16, then we get some same solution as given in reference number 19. And this is error table exact solution at the value of t is equal to 0.1 to 1, and HM solution at the value of t is equal to 0.1 to 1, and this is error exact solution minus a solution of by HM. This is error. And this is graph between exact solution and HM solution. Green line is showing the exact solution, and this red graph is showing HM solution, which is very clearly this is error graph. When the value of t is increasing 0.1 to 0.9, then the graph is increasing very minorly, and after 0.9 the error is increased very highly. And example number 3.2, this is also solved by the same process in given example 3.1. First of all, we can take one nonlinear quadratic integral equation, then exact solution and linear operator, nonlinear operator, and consider a homotopy for st is equal to 1, mth order deformation equation with this value, and using this process we have the value of r1, r2 and so on. And finally, we have the value of Rm for all natural number excepting m is does not equal to 1, and combining equation number 3.24 and 2.6, we get the value of the equation 3.27. by the using equation number 3.22, we have the
Dr. Kumar, could you please conclude, because we can able to understand that what you have done here. So please conclude.
Okay, sir. We get the value of x0, x1, and so on. Finally, we get the series solution. This is the comparison error table and graph between exact and HM solution, error graph, and conclusion. If in this paper we conclude that the homotopy analysis method is successfully applied to find the solution of quadratic integral equation. For the authenticity, we take two examples in section 3 and drawn the graph between approximate and exact solution. For the also shown the error table between approximate and exact solution with graphs and taking some references. Thank you, sir.
Okay, thank you very much. And we are quite late, so without any question, we move to the next.
It's okay. It's okay. Thank you, sir. Thank you, sir.
Yeah. So our next speaker is Krishnendu Bormon.
Yes, sir.
Yeah. Ajay, please you stop sharing. Dr. Kumar, could you please stop sharing your screen? Dr. Kumar, could you please stop sharing your screen? Okay. So, Dr. Bormon, please share your screen and start your talk without any further delay. Yeah, please.
Myself, Krishnendu Bormon, Department of Mathematics, Prabhat Kumar College, Kontai. My topic is optimal control strategy to Japanese encephalitis through a mathematical study. These are the outlines. First, give the introduction. Japanese encephalitis is a viral encephalitis, which is the now public health problem throughout the world. It is like the similar. It is similar to dengue, yellow virus, West Nile virus, and which is the spread by mosquito. According to WHO, about 24 countries of Southeast Asia and West Pacific region where Japanese encephalitis is endemic. And here we have studied, we have formulated a mathematical model and analyzed various control strategy for the prevention of the spread of the Japanese encephalitis. And here we also consider the environmental effect. These are the notation I have used in this paper. Let's go to the schematic diagram of this model. We have divided the human population into 4 classes, that is susceptible, vaccinated, infected, and recovered. Susceptible human goes to vaccinated human class through the vaccination at the rate of V1, and vaccinated human again becomes susceptible through the rate beta 1. And susceptible human goes to infected human class by the bite of the infected mosquito. Here B is the average bite by mosquito on human per day, and row MH is the disease transmitted dead from infected mosquito to human. ST is the total human population. Here a recovered human again goes to susceptible class at the rate of alpha. Here we consider the control that is the one is control is the medicine control. Here P1 is the medicine control, and R2 is the rate at which the infected human goes to recovered class through medicine control, and alpha is the effectiveness of the medicine. And new age is the 1 by new age, actually the infectious period of infected human. Next goes to the mosquito population. We have divided the mosquito population into three classes, that is the aquatic phase, susceptible phase, adult susceptible mosquito, and adult infected mosquito. The susceptible, the aquatic phase of the mosquito, we have considered its logistic growth. Here pi is the intrinsic growth rate, km is the carrying capacity, and here dA is the natural death rate of the aquatic phase mosquito, and P2 we have considered the P2, which is the insecticide spray control, and D is the rate at which the aquatic mosquito dies, and susceptible mosquito dies through insecticide spray, that is R3 and R4, at the rate of R3 and R4. This is infected mosquito dies. And susceptible mosquito goes to infected mosquito class through the when susceptible mosquito bites the infected human or infected pig population. And here rho HM is the disease transmission from infected human to susceptible mosquito, and B is the average bite by mosquito on human per day, and C is the average bite by mosquito on pig population per day, and rho HM is the rho PM is the disease transmission from pig to mosquito. And here I have considered environmental discharge. Environmental discharge means the daily wastage of daily wastage of household, open drainage, and the stagnant water where the mosquito growth increase rapidly. And also also we have considered the unhygienic environmental condition, which increase the growth of pig population. Here I also divide the pig population into three classes: the susceptible pig, vaccinated pig, and infected pig. Susceptible pig goes to vaccinated pig through the vaccination at the rate of B2, and vaccinated pig again become susceptible at the rate beta 2, and susceptible pig goes to infected pig class through the bite of infected mosquito. Here rho MP is the disease transmission rate from the infected mosquito to pig population, and C is the average bite by mosquito on pig population. And due to the environmental discharge, the pig population, susceptible pig population growth increase, and epsilon p is the coefficient of growth rate due to the environmental discharge, and PT is the total pig population, and DP is the natural death rate of human. And if you have considered on the above assumption, we have formulated this model. Here the rate of change of susceptible human, rate of change of vaccinated human, and rate of change of infected human, rate of change of recovered human, and rate of change of aquatic phase of mosquito. And this is the rate of change of susceptible mosquito and infected mosquito. This is susceptible pig and susceptible vaccinated pig and infected pig, and the ET is the cumulative density of environmental discharge. Here sigma is the growth rate of environmental discharge due to human activity, and HT is the total number of human population. We have simplified this model through considering some constant, where A1, A2, I have written this. I have calculated the equilibrium point. For this equilibrium point, we have two types of equilibrium. One is disease-free equilibrium, another is endemic equilibrium. The disease-free equilibrium is two types of disease-free equilibrium exist. One is the mosquito-free, that we did not consider that type of disease-free equilibrium point, and another disease-free equilibrium point is given by this E1, where E1 is H is not HB not 0 0, and this is the given by E1. This is a disease-free equilibrium point is feasible when these two conditions hold, and we have calculated the we did not explicitly find the endemic equilibrium point, that is the positive solution of the system of equation 12 to 22. By the next generation matrix, we have calculated the basic reproduction number. This is given by this 1323, and the we have considered a theorem, and that is the disease-free equilibrium E1 is locally asymptotically stable when the basic reproduction number that is R0 is strictly less than 1, and it is unstable when it is strictly greater than 1. The main part of this paper is we have considered the optimal control, because during the control we have considered the cost. So I have a objective function j, which is given by integration 0 to t is the final time, and a0, b0, c0, a1, b1, b2, a2, b3, and d0 is the weight constant. And here we consider the V1 is the vaccine control, P1 is the medicine control, P2 is the insecticide control, P2 is the vaccine control on peak, P3 is the medicine control on peak, and sigma 0 is the effort to reduce environmental discharge. We have solved this problem by Pontryagin maximum principle, and I have considered the control strategy. That is the strategy A is the vaccine control, and strategy B is the medicine control only, and strategy C is the insecticide spray. Strategy D is the all control, apply all control, but no control on peak population. And strategy is the to reduce environmental discharge, and strategy F is the combination of vaccine and medicine. Strategy G is the vaccine and insecticide spray, and strategy H is the vaccine combination of vaccination and environmental discharge, and strategy I is the medicine and insecticide spray control. And strategy J is the medicine combination of medicine and environmental discharge control, and strategy K is the insecticide spray and environmental discharge reducing control, and strategy LMN, and this is the combination of three control. Strategy L is the combination of vaccine, medicine, and insecticide spray, and strategy M is the vaccination, medicine, and environmental discharge reducing control. And and strategy P is the applying all control, and strategy Q is the applying no control. I have solved this equation and considering this optimal value of j by the principle of Pontryagin maximum principle. I have drawn this graph and shown that the vaccine control, this is the comparison of single control strategy together with all control and no control. This red, this is the all control, that is strategy Q, this is all control, and strategy P, strategy Q, this is the no control, and strategy P, this is the all control, and this is the strategy A, this is the vaccine control. And we have shown that when we consider the single control, the vaccine control is the best control, and then this is strategy C, actually the insecticide spray control, which reduces the mosquito population, and it is also effective optimal control to reduce the infected human population. I have shown this graphically represented graphically to reduce the for the infected human population, infected mosquito, infected pig, and environmental discharge. And in this slide we have graphically present the strategy, which is the combination of two control, that is F, G, H, I, and J. Here we also notice that the vaccine control, where the vaccine control is included, the infected human population is dramatically changes, reduces. And here in the next slide I have considered the combination of three control. Here you also that the vaccine control is the best policy, because when the vaccine is combined with another control, then the infected human reduces radically. And these are so in this paper we have formulated the model and studied the defined control strategy, considering the cost effectiveness to implement this control policy. And we have shown that the vaccine control is the best control to reduce the Japanese encephalitis infectiveness. And these are the references I have used for this paper. Thank you, sir.
Thank you very much. Thank you very much for your presentation, Dr. Krishnendu Borman. Okay. So, Raghavendra Singh, are you present?
Yes, sir.
Okay.
Yes, sir. Okay,
Yeah.
sir.
So our next speaker is Raghavendra Singh. So please share your screen and.
Sir, visible my screen.
Let
Hello.
us wait for a couple of moments. Till now, it is not visible.
1 minute, sir. Share my. Visible my screen?
No, no.
1 minute, sir. Full screen. Step up.
Okay, so without further wait, you can just mention what you have done.
Sir, 1 minute. Sir, without.
No, no. We can't see any slide.
Sir, 2 minutes given your time.
I think it is better if you just tell us what you have done, and that would be enough. And afterwards, you can send the slides to the organizer. There is not a problem.
Ayush! 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 अरे आयुष
Dr. Singh, without sharing your slide, you just tell us what you have done. That would be enough, I think.
सर लास्ट 2 मिनट्स हाँ देखो कहाँ से यहाँ से देखिए इधर 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 क्लिक कर योर इंटायर स्क्रीन इंटायर शेयर शेयर
Dr. Singh, without oh, okay, now it is visible.
Hello.
But we can, yeah, please.
Yeah, screen my show.
Yeah.
Yes. Good evening, all of you. Myself, Dr. Raghavendra Singh from Kanpur, working as an assistant professor in UPRT Prayagraj. My topic is about comparative study between neural network model and mathematical models for prediction of glucose concentration during the enzymatic hydrolysis. Abstract then. Glucose hydrolysis is the complicated the process due to the numerous and enzymatic initiative the process to take the place of the during the course of the hydrolysis when the it come concentration predictive model of the procedure contractive. Contractive the reduction is the kinetics to the board otherwise impossible to simulate it more standard the demonstrative approach artificial neural network are
Dr. Singh, there is no need to read your slide line by line. You just you can show your model and what you have done. Just mention that would be enough, I think.
extremely effective. The current the investigation was carried out the interior of the for predicted the enzymatic hydrolysis for the glucose as well as comparative to predict glucose. The obtained the result of demonstrated the neural network is the can be the valuable tool of the design the enzymatic using an artificial neural network. The neural network hope the indicative to the production glucose in the hydrolysis process and the compare there the prediction the experimental result obtained and the artificial compose the three layers in input layers and hidden layer and the output layers.
Dr. Singh, please do not read the slide line by line. Just present whatever you have done. You please show the model and come to the conclusion because we can read the slide.
Okay, sir. Okay, sir. Key parts the glucose in the hydrolysis and the next points the introduction the enzymatic glucose the hydrolysis and the purpose because to the dispose the cost of the increase in equivalent of the enzyme to but with the development the accurate mathematical model for the rejection and critical challenge and alternative approach to obtain the model of the incursion. Artificial neural network is the hidden incomplete to deal the non-linear problems. After the training and artificial neural network application, the biotechnological process and continuous. Artificial neural network is the glucose production, the various enzymatic hydrolysis conditions with the available experimental data and compare to results between the kinetic model in integers. Next, the theoretical model is the mathematical modeling is the enzymatic between the studies in the neural published work and mathematical model enzyme to enzymatic. Next, process the conditions to enzymatic hydrolysis. Processing values are reference and temperature the 15 to and 400 in enzymatic the time and 200 and pH value 4 point this values. And obtaining timing is 24 and pH value is the 5. And note EFPU is equal to filter the paper and unit IU is the international unit of the enzyme activity. The substance, the equivalence and effective subtraction, contraction and presence of the glucose as difference to values of. Next, the error of S naught is K of E and upon to escalate. The mathematical model developed the models was thinking of the glucose concept to the consider the usually and sync in the in other words the prediction size the reduction and particles is these values are given below. A fraction is the glucose enzyme the abiotic and institute practical surface and hydrolysis transference enzymes from the solution and particle surface is very rapid to that does not affect the hydrolysis rate. Production the negative effective rate of the hydrolysis and enzyme activities particles sitting in the during value. This model is the given different equations two stage of the process. In the first stage of the process, the second stage is the absorbed the enzyme return to solution and the equations would you different. Rest of the equations are derived to first stage and the alpha phi and a model of the parameters. They are following the equations of the second stage of this. This model is the artificial neural network in developing model. This is the glucose the loading and the non-glycation and glucose the initial concentration and hydrolysis to glucose models. The Kd upon 3 T minus T1 is equal to Kq is the values of where 1 upon 3 Z is equal to Y e power 1 by 3 and the I naught I1 and I2 operation to reflect definitions of the difference conditions. Verification of the conduction data is the present work is the prediction the capability models of the predict values of these values. Equations of 6 and 7 and 9 these equations solve model the prediction the enzymatic hydrolysis. This studies the construction, the effective parameters, hydrolysis, and the select the parameters, the development using the artificial neural network, performs the validity predicted, obtain the are verified to RSM. RSM is the very values of the reflection model of the developed using the artificial neural network based on the experimental data of the provide the literature previous studies. Review the literature of the values of the algorithm, use the analyze signal and noise ratio given to data. The concept the power is not successful with the coding is the network. The genetic is the values of saluting in the control algorithm and typical power and the management interference. It is the necessary trend of artificial neural network is the way to a back of propagation as the cost of MLP training the being the applying to input vector. Two input layer having the network processing in 19th. Conclusion. According to finding the study, neural network is the volume of 2014 successful attempt to write those in conditions the compared to RSM model and ANM model. To clearly to accurate between the estimation, the simple arithmetic operation, the neural network model is the comparative. It is the associative neural network model in service and the link between the isolated experimental data and the result, the enzymatic between the independent investigations too. That is repeat through references of the nets and nest references these values of nest references are. Thank you.
Thank you
sir.
very much. Thank you very much for your timely presentation. And with this, I thank all the speaker of this session, and I also thankful to you for being present throughout the session. And so let us thank all the speaker, and I can say that this session is over.
Thank you, Professor Banerjee, for conducting the session nicely. And also thank you all the participants. Tomorrow we'll meet before 4 p.m. and good night to all of you.
Good night, sir.
Good night, sir.
Good night.
Good night, sir.
Thank you so much, sir.
Thank you, everyone, and good night.
Thank you, sir.
Thank you, sir.